you do get from professors, mentors, bosses, parents. And they would direct you towards pathways that they think you may do great in. But who knows you better than yourself? You must continue seeking guidance from experts. For at the end of the day, your own evaluation about your potential would help ascertain what things to remain focused at and what factors to simply be given less priority. All right, before we call Advait, let me just go over a few pointers and we'll go to introducing Advait to the attendees. A few informational pointers. Feel free to post your questions on the chat window. We'll make sure to address them either post session or offline. Please reach out to us if we are not able to address them even after the session. The event is being live streamed and recorded for online and offline viewing on YouTube. YouTube link has been, oh, well, it's not working. I just, Puneet,
It's
are we
working.
able to?
Yeah,
it's working. Perfect. Now. Has the link been shared already?
I'm going to do it.
In the chat window? Okay, perfect. Thank you. It's just so that you can share it with those who were not able to register it with this, they can still, attend the session. The participants will be muted during the talk. Please keep the videos off during the whole webinar. In case of any unnecessary disturbance or interruption during the talk, that person will be removed immediately from the session. Okay, let's begin the session. All the way from Maryland, USA, Advait, thank you so much for your patience. It's past 12:30 in the night. I'm going to hand it over to you as soon as possible. Let me just quickly give a brief introduction about you to our attendees. Advait Madhavan is currently a faculty specialist at National Institute of Standards and Technology, University of Maryland. After receiving PhD from University of California in the year of 2016, he continued his duration as research specialist for another year in the same university. He wanted to pursue additional research in his area of expertise, so he did postdoctoral fellowship at NIST for 2 years. His interests lie in various brain-inspired approaches to computation, such as temporal, analog, and stochastic codes. His expertise lies in VLSI with the objective of building chips to interface with emerging technologies in order to realize these unconventional computing paradigms. He has co-authored several publications. I'm going to just mention a few. A configurable CMOS memory platform for 3D integrated memristors, vertical integration of memristors onto foundry CMOS dies using wafer scale integration, race logic, a hardware acceleration for dynamic programming algorithms. And when we talk about honors and recognition, in 2015, Advait's research papers were chosen by IEEE Micro as one of the top picks from computer architecture conferences. Just to give you an idea, IEEE Micro's yearly issue collects some of the year's most significant research papers in computer architecture based on novelty and potential for long-term impact. He also received ASPLOS Best Paper Award for Boosted Race Trees for Low Energy classification in April 2019. How amazing the journey has been. Seems like Advait exhibits an analytical mind that never stops exploring, probing, and reaching his best findings. Over to you, Advait.
All right, Prerna, thank you for that introduction. I'm just going to share my screen. Can I share my screen here? All right, it says.
Yeah, so what I'm going to do, I'm just making you co-host. Now you can do it. Try.
All right, that works. Okay, so I hope you can see that.
Yes, you can do it.
All right. So thank you for that introduction. I'm gonna start right in here. So what this talk is basically about is about the history and the future of computing technologies, right? And we're going to start really early. We're going to start somewhere around the 1950s, and we're going to go all the way up to where we are now. And then I'm going to just talk about some ideas about future computing schemes that we may have. Now, so one thing to realize that this is about general purpose computing, all right? So I just wanna jump right in. This is the first slide here. And what I basically want to first do is is just, look at these two figures, So this is what a 70-year long exponential looks like. So basically on the left, you have a room that is the size of 1,800 square feet. And the room is basically a machine. It's a computer that weighs about 30 tons, takes about 150,000 watts of power, and does about 5,000 operations a second. And this machine is called the ENIAC, and it was built in the 1940s and the 1950s by the US Army research labs for calculating trajectories of missiles. And if you fast forward 70 years, on the right, you have this tiny iPhone that somebody's holding in their hand that weighs about 200 grams, is about 6 inches, and takes up only about 6 watts of power. Not only all of that, if you look at the number of operations per second, there are 9 zeros of difference between the operations on the left and on the right. So, if this does not blow your mind in terms of just the sheer, magnitude of performance improvement that we've had over 70 years. I mean, if you take this phone and give it to the lady there on the left, I mean, she will not believe this. I mean, it will sound like science fiction, and basically the point of this talk is to understand how we got from there to here, how we got from the left to the right. All right. And how we're going to do that is we're going to basically, rest on some fundamental ideas in computing and in VLSI. All right. So let's just basically start. And the first question may seem like a very sort of stupid question, but the question here is, what is a computer? Right. And you may think that, the thing that you're sitting in front of right now, which is, either a desktop or a laptop or something like that, it's a computer, and that absolutely is a computer. But what about some other things? What about things like this, like the smartphone that you may have, or, a server, maybe a Google server or a Facebook server where all your information and data is going in and out of all the time, right? Is that also a computer? And if we, stretch that to something even more sort of simple, just a calculator, something that you may use, at work or at school or something like that, is that a computer? And if we go even sort of simpler, like an abacus, is an abacus a computer? And basically the point of this slide is that it doesn't matter what the physical instantiation of the computer is. It may be in silicon or a mechanical machine or even just a toy-like machine like an abacus. But what a computer actually is not the physical instantiation, but it's actually a organizational structure, a hierarchy of information processing, right? And this hierarchy is called a computing stack. And this computing stack is basically a very important idea here. And I'm going to take an example of this very simple abacus and just sort of go through what this computing stack may mean, right? So at the bottom of this computing stack are the physical devices that actually do things, right? For example, in the abacus, you have beads, and these beads move on strings, right? And those are the physical devices that actually do things. Now you can think of these sort of circuits as the strings, and you're actually sort of moving these beads on these strings and doing computation with them. And if you notice that the encoding is how you interpret the information on these beads. You can say that the black beads encode a value 1, the dark blue beads encode a value 10, the light blue 100, the white 1000, and so on and so forth. And by that interpretation of these beads, you sort of impart encoding onto these beads, and then you can arrange them into these large architectures. You can have like this square sort of wooden structure. If you had more beads, you could encode more information. If the wooden structure was bigger, you could, do larger scale computations. And you can just go on YouTube and look at the different kinds of crazy algorithms that people have to do all sorts of things on an abacus. You can do addition, multiplication, division, square root, exponentiation, all sorts of interesting algorithms you can do with this. And if you just, so basically you can map this sort of some, a toy as simple as this to basically a computing system where the physical devices at the bottom are actually field effect transistors, FETs, like CMOS transistors. The circuits are built out of VLSI. They use this sort of Boolean digital encoding schemes, right? When you have a high voltage, you call that a 1. When there's a low voltage, you call that a 0. And then at some high level, you have all these various architectures, and by architecture, I mean the sort of broadest possible, definition of architecture, like, adders, multipliers, comparators, memory units, shift registers, and going as high up as instruction set architectures and all of that. And then on top of that, you have like a software which speaks to the architecture, So one very important aspect of this computing stack is abstraction, which is that the person sitting on top of the stack does not know what's happening below. And that person does not know what's happening below. If every time you go, if every time can you hear me? All right. So if every time you wrote a piece of code in software, if you had to worry about how the transistors were switching or what the electrons were doing, I mean, that would become a big problem, right? So basically, abstraction is going to hide every lower layer in the stack. So the software interacts with the architecture, but it doesn't care about the encoding. Similarly, the architecture interacts with the encoding, and the encoding interacts with the circuit, and the circuit interacts with the physical devices, right? So basically, the point of this slide is that we are going to use this computing stack to understand what's happening. And we are going to look at this from the perspective of the three main sort of forces that are guiding this industry of computing. Now, one of them is basically the VLSI industry on the left. On the right, you have a variety of different kinds of applications and their related computing architectures. And on the bottom, we have some, novel ideas in biology, physics, and mathematics. So what we're going to do is we're going to first look at the top two and not look at the bottom. And at the end, we look at future computing architectures based on these ideas, right? So this is how the talk is going to be structured. We're going to take this computing stack and we're going to take these two important ideas, VLSI and applications, and we're going to see how these two ideas, using these ideas as like a scaffolding, we are going to look at the chronology of the figure on the right. So the figure on the right is probably one of the most important figures in computing. This is basically 42 years of microprocessor trend data that's been collected by Stanford. So these folks have been collecting this data over the last 50 years, basically, right? And as you can see, the x-axis is linear, the y-axis is a log scale. So as you can see, every increase on the y-axis is an increase of 10x. And as you can see, the transistors have continuously increased, which is basically showing you exponentially more number of transistors in your chip every year, right? Now you're also seeing that the single-threaded performance of your computing system is not growing as fast as your transistors. It grew exponentially for quite a long time, but then it slowed down, right? The clock frequencies of your computers have also slowed down, right? You have 3.5 gigahertz computers, 4 gigahertz computers. I mean, you don't have a 20 gigahertz computer, right? The frequency is saturated. So, that's also an important sort of trend. And the power also begins to saturate around the year 2000, while the number of cores begin to increase. So basically, we're going to use this figure as a scaffolding, and we're going to go through decade by decade, and we're going to look at representative microprocessors of each decade, and we're going to see how this development happens, and we're going to give some VLSI understanding of why this development has happened in this way. All right, so let's just jump right in. First, we're going to start with the ENIAC, which is again, not in the 70s. So we're going even way further behind. So 1940s, 1950s, right? Now, at that time, VLSI did not exist. There was no integrated computing hardware. CMOS transistors were not invented at that time. So there were vacuum tubes, which are like transistors, but they're like bipolar transistors. And so the physical devices at the bottom are vacuum tubes, diodes, relays, capacitors, and resistors. And that was still implemented with digital logic. So you could still use things like flip-flops and counters and so on and so forth. but the encoding was not simply binary. It was binary coded decimal encodings. And if you look at the figure on the top right, that is basically showing you all the wires that have to be plugged in and out of this machine to program it. So it's not automatically programmable like, you can program computers these days with, by just sort of writing code. I mean, you had to, four ladies that you can see on the top here are actually the programmers of this machine, and they used to spend 1 or 2 days basically, uh, connecting these wires in the right way. And this machine, again, just to sort of reiterate and establish a baseline, this used to do 5,000 operations per second and used to take up 150 kilowatts of power. And this was used to calculate the trajectories of missiles just after World War II. And 1 hour of this ENIAC machine would replace 2,400 hours of a human sitting down and actually doing the math for what the trajectory of the missile is going to look like. So, in spite of how annoying it was to program this machine, it was still 2,500 times superior to a human calculator. All right. So that being said, let's now jump quickly by another 20 years and let's get to the late 60s, early 70s. And this is when Intel basically began. And we're going to look at this period. And as you can see, 1 core, low power consumption, low frequency. So let's see what we have. So this is one of the first integrated microprocessors ever built. And this is called the Intel 4004. And this was basically used as a calculator for just basic arithmetic operations. And it was sold to like a Japanese company called, I forget the name. It's something like Busycom or something like that. And those guys basically sold calculators. And at the bottom, you have these, at the bottom of the computing stack, this was basically using 10 micron CMOS transistors. So, now we have 7 nanometer FinFET. So this is like 10 microns, so they're huge, huge transistors that work at 15 volts VDD. And the entire thing had only 2000 transistors, right? But this was still able to perform 92,000 instructions per second at 1 watt. So if you compare that to the ENIAC, it's already almost 2 orders of magnitude more instructions at 5 orders of magnitude less power. And that's just because of the fact that these folks at Intel were able to find a way to integrate multiple transistors on one die, right? And if you basically look at it, this was a 4-bit computer that was completely digitally encoded with Boolean logic. And the architecture was kind of like a Harvard architecture, but not really, because it had like a single multiplexed bus, which had, even though it had sort of separate memories for program data and basically the actual processing data, it still had a single multiplexed bus. And if you see this, this is like it's like a 16-pin DIP package, so it looks really, really primitive basically. And so this is 1 watt of power at 740 kilohertz. It doesn't even reach a megahertz. So this is really, really old technology, almost a sort of beginnings of integration, right? Now, if you just fast forward a decade, the industry is just sort of getting started and they're beginning to, hit their stride. So what happens? So we're going to look at now the Intel 8086. And for anybody who's familiar with this field, the 8086 was one of the first 16-bit microprocessors, and it was extremely widely used. And if you look again at the bottom of the stack, 29,000 transistors. So that's 1 order of magnitude more than the first 4004 that we looked. So in a decade, you can put 1,000 times, you can put 10 times more transistors on the same chip. And the VDD is dropped to 5 volts, and the transistor size is again dropped from 10 micron to 3 micron. What has not changed is the fact that it's still digital primitives and a Boolean logic and a digital encoding. But this was again representative of the first x86 instruction set architecture. And the x86 architecture is still used, in the i7s and i9s of today. But this was one of the first processors to have this x86 instruction set architecture. And again, as you can see, the size of this thing is scaling up from 16 pins to 40 pins, but such a primitive machine was still able to run basic operating systems like DOS. Even the IBM PC, which was the first PC that was ever used for basically usage inside your homes, had this processor in it. And in terms of applications, it was also used by NASA for their controlling of their Discovery, which is a rocket that they sent into space basically. And if you can look at it, this is 330,000 instructions per second with 1.8 watts of power dissipation at 5 megahertz. So they've breached the megahertz barrier. They're now at 5 megahertz, but the power dissipation really hasn't changed much. It's just gone from 1 watt to about 2 watts, but the number of instructions has really gone up from the 4004 to this guy, right? Now let's take one step forward again, 10 more years. And as you can see, now we are beginning to see some really good exponential development, right? There are a lot more number of transistors on a chip. There are now 1,000 times more number of transistors on a chip. The single threaded performance is going up exponentially. The frequency is going up really fast. So all these different things are happening. And one very important processor of this time is called the DEC Alpha. And this processor was just way ahead of its time. Like it's unbelievable how ahead of its time it was. Basically, it does 400 million operations a second with 56 watts of power dissipation and 330 megahertz. So it's basically 2 orders of magnitude faster, consumes almost an order of magnitude more sort of power, and is just extremely fast. And this is able to integrate, 9.3 million transistors on a chip with half micron technology with a VDD of only 3.3 volts. And in the early 90s, this was a 64-bit processor. So that's pretty crazy. And not just that, because they had all these extra transistors, architects were trying to utilize these excess transistors to be able to maximize the performance that you can get out of these systems. So you had these super pipelined, super scalar architectures, which had long, deep sort of pipelines. They can sort of issue multiple instructions in one clock cycle. And, so this was really an ahead of its time processor. But the important thing you have to kind of notice here is how sort of power hungry it is and, what kind of operations it can do. And it can also boot operating systems like Windows, NT, and Unix. So, now we are getting into stuff that we're familiar with even these days, Windows operating systems, Linux operating systems. And this was built on a this was built for a general purpose computation. And this was one of the first computers that breached the 1 micron transistor barrier. So this is like, these are like half micron devices. So if you've been paying attention, you would have noticed this behavior in VLSI scaling that is underlying this whole thing at the physical devices level. And the scaling is affecting the performance of your system, right? So now we're going to understand what is basically happening here. So now this sort of regime from the 70s to the 90s is called classical scaling. And why it's called classical scaling is because this is the first way people used to think about scaling. And how do you think about scaling? So you have a scaling factor in this we're calling this factor S. And the scaling factor S was about a square root of 2, essentially. And this factor means that with every process iteration, the width, the length, and the thickness of the transistor would go down by a square root value. So again, on the left, you can see the figure. There's a length of the transistor from the source to the drain. You have the width of the transistor, and you have the thickness of the oxide as well. Right. And so basically, if your scaling factor is a square root, then the area of the transistor is halved every iteration, right? So that's the main point here, that basically the width of the transistor goes down, the length goes down, the oxide thickness goes down. But if you remember, when we moved from the 8086 to the DEC Alpha, we just went from 5 volts to 3.3 volts. So that wasn't a major supply voltage change. And why there were no major supply voltage changes at this time was because you had to still interface with older technology. Now what's happening here is that your gate capacitance scales as only 1 over S, while your saturation current scales as S. So your capacitors are getting smaller and smaller, but the saturation sort of current that is driving that capacitor is getting much faster. So your capacitor gets square root times smaller while the saturation current increases by square root times. So the speed at which this capacitor can be charged goes up by S square. So the frequency goes up by S square, right? And as you can see, the VDD remains the same. The C gate goes down by 1 over S. Now, the N factor in the dynamic power equation there is the number of transistors that you can integrate. And the point there is that if your width and length of the transistor scales down, meaning that the transistors become square times smaller, then you can integrate square times more transistors in the same area. And therefore, your dynamic power goes up by S cube. So if you look at this transition from the 70s to the 90s, we began at 740 kilohertz and we ended up at, how many megahertz was the DEC alpha? You guys paying attention? 330 megahertz, right? And that's a really large frequency increase. And that goes again with a dynamic power increase from 1 watt to 56 watts, right? Now, as you notice, this cannot keep going on, right? You cannot keep having the dynamic power increasing and the frequency increasing. Why is that? Now, that's because of physics. And why that's because of physics is because of the fact that dynamic power dissipates heat, and there's only a certain amount of heat that you can remove per unit area, right? You can have a fan that's sort of blowing air on it, that has a certain heat removal ability. You can have some sort of liquid kind of cooling, or you can even have, ultra low temperature kind of cooling. But commercially, there's just a rule of thumb, which is 200 watts per centimeter square. You cannot remove more heat than 200 watts per centimeter square effectively. So that dynamic power cap is now a problem. And so you just cannot do this scaling anymore, right? So how did the industry deal with this issue of not being able to continue the scaling, right? So now we get to this period between late 90s to early 2000s, which is, we are looking at this part of the spectrum. And here we look at this Intel Pentium 3. And as you can see, the Pentium 3 is only 32 watts of power, though the clock frequency has gone up from 330 megahertz to 1.4 gigahertz, which is insane, and does 2 billion instructions per second compared to your 400 million instructions that your DEC alpha was doing. And this is doing it with 45 million transistors at 130 nanometer CMOS with a VDD of 1.45 volts. So that VDD of 1.45 volts should ring a bell, because earlier it was 5 and 3, and now it's really 1.45. So, there's this sort of drastic reduction in VDD, Now, if you again notice, this is a 32-bit computer. Intel was building 32-bit computers at this time. DEC was 64, so, that's why I was saying it was ahead of its time. And again, this is the x86 instruction set architecture. And this guy had 370 pins in a flip chip bonded pin grid array. And I'm sure some of you are even old enough to remember this stuff. This is, you could play games on this. You could play, Doom or Quake or, all these kind of games. I mean, you could do web surfing. Windows and Unix could be easily installed on this stuff. And this was basically one of the first deep submicron technologies, right? Now we're going into 130 nanometer technologies. And this was also built for general purpose computation. Now let's take one step further, 2000s to 2010s. And one important thing to notice here is now we are beginning to slowly saturate in power, saturate in frequency, but the number of cores are going up. So, that's an interesting point to just kind of notice. And the representative processor of this time is this Intel Core i7, right? And this guy now has 1.1 billion transistors at a 32 nanometer CMOS technology node with VDD of 1.2. So this is a 64-bit machine, and Intel's made all kinds of versions of this, from 4 cores to 48 cores. And this machine has a 1155 pin interface, and it's called a land grid array. So it's all the way at the bottom, and the whole chip just sits on this land grid array. And this can basically run anything you want. I'm sure that a lot of you have your i7s or i5s and stuff in your computer now. And this guy does 300 billion operations per second with 130 watts of power dissipation. And this runs at 3.6 gigahertz, right? But if you look at the actual die photo of this, you can look at you can actually see this core-based architecture. There are, multiple different cores. There is a graphics side of it, there's a memory controller side of it, there's an L3 cache. All this stuff is integrated into one die. So this is, a really, advanced piece of technology. So how did this happen? How did, 5 minutes ago we were saying that you cannot scale up the power. How are you able to get so many more operations without scaling up the power, right? So this is because of Dennard. So Dennard is basically an IBM engineer in the 70s, and he basically realized that there's another way of doing scaling. And this way of doing scaling is that he called it constant field scaling, because as your transistors get smaller, if the supply voltage is still very large, then the fields inside the transistors become extremely large, and those fields can sort of cause breakdown of the oxide and breakdown of other of the silicon inside the transistor. So he basically said that what we should do instead is reduce the VDD concomitantly as we go from one process node to another node. So now, not only is the width, the length, and the thickness going down, the supply voltage is also going down, right? And that has important implications. Why does it have importance? So the first implication is that the saturation current of this thing also begins to go down. Earlier, the saturation current was going up, right, by S. Now it goes down by 1 over S. And as a result of that, the frequency doesn't scale up by S square, it scales up only by S. But an interesting thing to note here is because you can put square number of more transistors in the same area, if the VDD goes down also in the equation of dynamics or of power, you have VDD square. So that VDD square cancels out the more number of square transistors being added per unit area. And therefore the dynamic power remains fixed. So basically he was able to find a way to cap your dynamic power while still being able to increase the frequency and still being able to add square number of transistors in the same unit area. And when computer architects are given free square number of transistors, they do all sorts of interesting things with them. Like we saw, they build i7s with basically so many more cores on them, right? And now why are there more cores on this computer? Now there are more cores because of the fact that what happens is we've just looked at the VLSI side of it. Now, if we also look at the application side of it, it turns out that extracting maximum performance by increasing the clock frequency is not optimal. Why is that? Because if you have to increase the clock frequency, with that you have to do a lot of other things. You have to make sure that all your processing that is happening in the chip meets these sort of timing margins. You have to also make sure that you don't hit a memory wall. You don't hit this instruction level parallelism wall, which is basically the fact that the applications that you have are actually parallel in nature. And because they are parallel in nature, if you increase the speed of if you only increase the frequency, what ends up happening is you are only increasing the serial operation speed. You are not increasing the parallel operation speed. So instead of spending a lot of engineering effort into making one core go from 4 gigahertz to 10 gigahertz and make these sort of timing margins small, invest all of this effort and money, what you could rather do is make another core that's working at 3 gigahertz, and that core is able to exploit this parallelism. Because if there's some sort of parallel task that has to be done, then that parallel task can be offloaded onto another core, and that core can perform that task while the first core is doing something else as well. So that's basically the essence of why this multi-core operation happens, right? Now, we're going to again go back to the early 90s, and we're going to look at this core-based approach. And this core-based approach spread to a different application space, right? And this application space can be thought of as graphics applications. And therefore, we're going to look at this NVIDIA GPU, which is this GeForce 256 GPU. And now, what is this? Why? So basically, what is happening here is that this is an application that demands parallelism, right? Because you have a bunch of pixels on a screen, you want to sort of render all these pixels. And it turns out it's that the same amount it's basically the same instructions that are happening on multiple pieces of data, because what you have to sort of render on the screen is the same thing. And this doesn't have to be general purpose. You don't have to do all kinds of operations. And I mean, you don't have to do, I mean, the whole space of operations that you can perform is much smaller when you only have to sort of render pixels on a screen. And if you see, this is 23 million transistors in a 220 nanometer CMOS technology node with, again, a 3.3 volt VDD. And with 100 watts of power and only 120 megahertz, it's still able to do 480 million pixels a second with 10 million polygons a second. And again, the architecture here is SIMD, that means single instruction, multiple data. So basically, the graphics application is a specific application that can exploit parallelism effectively. So it makes sense for this kind of an architecture to have multiple parallel things of the same type. So, you have 4 sort of pixel shaders, 4 texture mapping units, 4 render output units. So basically, all these units are performing the same task on multiple pieces of data, which are the pixels, right? So, so this is another sort of application-based pull to this whole industry that, exacerbated this multi-core kind of idea, right? And if you push this to just day before yesterday, when this beast came out, this is a NVIDIA 3090 RTX, which is basically the sort of fastest GPU on the planet right now. And this is made out of 8 nanometers Samsung FinFET transistors, which has a VDD of less than a volt. It has 28 billion transistors on a single die. It's 64-bit. It runs on CUDA. And the first one that was released in the early 90s had 4 pixel shaders. This guy has 10,000 pixel shaders, right? And why it has 10,000 pixel shaders is it's not using, 220 nanometer technology. It's using 8 nanometer technology. And plus there are a whole other wide range of, developments across the whole stack that have caused this, tremendous performance improvement. And as you can see, this is not working at 10 gigahertz. This is still 1.4 gigahertz, which is still slower than your CPU in a way, but it still performs, it still does 350 watts of power and is giving you almost 30 tera floating point operations a second, right? So again, this is part of this whole Dennard scaling, power dissipation remaining capped while still being able to provide more number of transistors, and therefore allowing architects to be able to do all sorts of interesting things, which leads you to this kind of technology, right? So now we're going to come to the scaling regime in which we are in right now. And this scaling regime is called leakage limited scaling. Now what happens is you cannot endlessly drop the VDD. What happens is after a certain point, the VDD has to remain fixed because the threshold of the transistor begins to drop. So basically, if you drop the VDD, you have to also drop the threshold of the transistor. But what happens is once you drop the threshold beyond a certain limit, because of the way the current scales down, it has a Boltzmann scaling law of the best case being 60 millivolts per decade. What that does is when your transistor is turned off to sort of 0 volts, it's never sort of 0, it's some small value of voltage. And if your threshold voltage is very low, that still means a large amount of current. And if you lower the threshold beyond a certain limit, you're only going to waste energy in leakage. And because you're going to only waste energy in leakage, people did not reduce the threshold voltage beyond a certain limit. So the threshold voltage is fixed now around, I don't know, I think it's somewhere around 300 millivolts or 350 to 400 millivolts. But people don't lower the threshold voltage any lower than that. Now, since the threshold voltage has been capped, the VDD also has been capped and the VDD does not change. So again, if you look at this leakage limited scaling, what happens is your supply voltage is capped. The saturation current now gets capped. It's just a fixed saturation current because it's WVDD over thick oxide, and everything is, VDD is capped. W over thick oxide both scales by 1 over S. So you just end up getting 1. And the frequency can still be scaled up, but now your dynamic power scales up by S square, right? So now we've hit two walls, right? One wall is your dynamic power wall, right? You cannot remove more than a certain amount of heat from your system. So your system is capped. So you can put more transistors in your die, right? But you cannot switch them, because if you keep switching them, that's going to incur a lot of dynamic power, and therefore this is going to be a problem, right? So this has led to this whole new avenue of computing architectures, which is called accelerator architectures. And what accelerator architectures are architectures in which this activity factor of your circuits are low. So you don't have high activity, and these are very, very specifically designed, carefully designed circuits, which ensure that by using clever tricks, you can keep really low activity factors. And by keeping low activity factors, you can still improve the performance of all these various interesting applications that you may have that are neither general purpose applications, nor are there, very, very specific sort of GPU like applications or something else. I mean, you have extremely application specific things that you may want to do, for example, machine learning, right? And therefore, when you begin to build things for those architectures, you can tune your circuits in a way that the activity factors end up being really low. So one example we're going to take a look at is this thing called a TPU, which is a tensor processing unit that's built by Google that does all the backend for all the machine learning stuff. So when you type anything on Google, the sort of natural language processing of your statement is happening on a machine learning backend, which is happening on this sort of TPU. And what is a TPU? So as you can see these figures for what a TPU is. So on the left, that's a TPU a chip on like a board, and on the right you have a TPU pod, and each TPU chip takes about 40 watts of power. It's only 700 megahertz, but it gives you 23 tera ops per second. And why does it do that? Is because it's not general purpose. It cannot do everything. It can do only specific applications built for machine learning, which is matrix multiplication. It has very specialized hardware in it, which is a systolic array, which is 128 by 128 of size and has all these 65,000 elements in it. It's not 64-bit because machine learning does not need 64-bit for inference. It needs only 8-bit. So it's basically specifically tuned for this application, has 2 billion transistors in it, and is made in this 28 nanometer TSMC foundry kind of process, right? So basically, what is the whole point? The whole point is there's a journey from CPUs to ASICs. And what is that journey? There's a journey from flexibility, that early on you wanted one computer to do everything. And because it's flexible, it cannot be efficient. And as you keep shifting from your basically from your flexibility to efficiency, you basically start doing applications that are more niche, like maybe graphics processing, maybe compute acceleration if you're going to use FPGAs, web search, 5G communication, machine learning. And basically, as you move towards the right on this, your flexibility goes down, but your efficiency goes up. All right. So this is kind of the whole big picture of what has been happening in VLSI and computing, and how we've gone from one core to basically ASICs that have now 65,000 cores, while each core is essentially a processing element that's doing this matrix multiplication in a TPU, right? Okay, so I have about 5 minutes left. So I'm going to try to blaze through this in 5 minutes now. So the final thing that I find the most interesting, to be honest, amongst all of this, is this new novel ideas from biology and from physics. And now let's just go back to where we were in the 1940s, right? In the 1940s, late 40s, I showed you a picture of a room. And this room was this giant room, which was like 1,800 square feet. And there were 4 people hanging around inside it, trying to program this machine. And this is today's room. If you look at, this is basically the back end of a Google TPU pod that handles all your machine learning. This has 64 TPU boards, 4 TPUs per board, 100 watts per TPU. So this whole structure that you see in front of you now takes 250 kilowatts of power and has 100 billion transistors in it. And this is probably one of the most efficient computers that we know now. And this provides 10 raised to power 16 operations per second. That's 11 petaflops of operations per second. And this is for machine learning, training, inference, and acceleration, right? And now I'm telling you that this is the most efficient computer that we know, right? But is that really true? Is that the most efficient computer that we know? I'm going to argue that we have another computer that we all have that's more efficient, right? And that's this guy, right? This is in your head. It's inside your skull. It weighs about a kg, less than a kg. It's tiny. It consumes only 20 watts of power, not 250 kilowatts. It's got 100 billion neurons, and it has a performance that's 3 orders of magnitude more, 10 raised to power 19 operations per second, at 5 orders of magnitude less energy cost, and probably even 5 orders of magnitude less weight, right? And these are happening with neurons that operate at a millisecond time scale, not at a picosecond time scale that CMOS chips operate at, right? So how does the brain do this, right? How does the brain do this? So basically, my contention is that the future of computing is going to be trying to understand the brain, trying to understand what the brain is doing and how is it doing this, and how we can take ideas from the brain, put the brain in a computing stack, understand what the brain is doing from a computing perspective. Look at the devices. What are the devices? They are neurons, right? Can you build equivalents of neurons in CMOS? Can you make analog neurons? Can you make digital ones? Can you make hybrid ones with analog and CMOS and new technologies, right? How does the brain encode information? So you can't just do this in like a black box. You know, you have to go speak to the biologists. You have to speak to the physicists and the chemists, and you have to understand the chemistry of the brain. What is the spiking rates? How it's encoding information? What are the spike times, right? And then you can put that onto an architecture that is a machine learning architecture that would be look like a fully custom ASIC in which you would have to route neurons in a certain way. And the sort of high level applications that can be mapped to this are cognitive applications like, you know, image recognition, sound recognition, all sorts of other, you know, kind of crazy machine learning applications that you can imagine. So this is what we've been working on in our groups. And one of the most interesting things here is, you know, this kind of analog computing by trying to be inspired by the brain. And so what is that? So, you know, so I'm just going to give you 2 or 3 very simple examples. One is, instead of doing vector matrix multiplication with digital circuitry, we all know that Kirchhoff's law is V is equal to IR, which is same as GV is equal to I, where G is the conductance, that's 1 over R, right? So if you apply the right analog voltages and you multiply with the right G's, you get an output of I. Now that is natively performing matrix multiplication, because one wire is going to take the multiplicated values from the conductances and it's going to sum them all on the output line. So that multiplication and summing happens naturally in physics. You don't need to build this computing architecture around it, because the physics of, I mean, you don't have to build this sort of digital computing structure, because the natural physics of the operation automatically does what you want it to do, right? Another approach is, if you imagine spiking activity in the brain, you can think about it as rate coded spiking activity. You can convert that to pulse width modulated digital signals. And one very simple example you can take is that if you put these uncorrelated pulse width modulated bit streams into a simple AND gate, that performs a complex operation like multiplication for you. Now on the extreme right hand side, instead of thinking about the brain as encoding information in spiking rates, if you think about it as encoding information in spiking times, what happens is a simple OR gate can perform a min operation and an AND gate can perform a max operation. So this is basically where the future of computing is going, in my opinion, trying to understand how the brain works, placing it in a computing stack, and being able to bridge this gap between the software and the basic hardware in a way that these higher level algorithms and primitives that you want to implement in high level software are directly implemented in the physics of the operation for you. And this is where energy efficiency lies. And energy efficiency is one of our main issues, as we've already seen. You know, taking heat in and out of a system is a big pain, right? So that being said, this is the summary slide, and I'm ready to take any questions. If there's anything that you guys should remember from this, is that a computing stack is very important. the whole movement from the CPU to the ASIC is essentially a trade-off of flexibility versus efficiency. And VLSI applications and new ideas like biology, physics, and mathematics are things that are going to push computing into where it's going to go. All right. And with that, I'm going to end. Thank you so much.
All right. Thank you, Advait. I see a lot of people actually. Are you there?
I'm here. Yep.
Okay. Okay. Sorry. I thought
I can keep my slides on if somebody wants to look at the slides for a little bit more. I mean, yeah, please feel free to ask questions.
So Advait, basically the questions are on the chat window. Maybe if you want to take it, you can take.
All right, sounds good. I'll do that. Please share slides. Difference between operations per second and core frequency. All right. So basically, core frequency is just what is the speed of your clock, right? So a clock is basically a tick that happens every time, right? Now so basically, if your clock goes at 10 megahertz, then you have a certain number of clock ticks that happen per second, right? Now the number of operations per second is how many operations are happening per second, and that may not be the same as your clock frequency. In old processors, that was the case because you could do only one operation per clock cycle. But now you have super scalar processors, you have out of order execution, you have all these tricks by which the parallel nature of these architectures, you can essentially dispatch multiple operations in one clock cycle. And because you can do that, you can get a much larger number of operations per second through this parallelism. So I hope that answers your question about what the difference between operations per second and core frequency is. Isn't this going back to analog signal processing, taking and merging that with digital computing? Yes. So analog signal processing is, noisy. And the big issue with analog is that you have all kinds of noise that can interfere with your system. And one really good feature about digital computing is that it has high noise margins, and because it has good noise margins, you can make systems that are reliable and don't fail, basically. So analog computing is important. In my opinion, it will play a big role in the future, but it will not replace 64-bit floating point digital computing. That's something that is error tolerant. It's an industry sort of standard. But there are specific applications where analog computing can actually do really well. So please explain how multiplication is performed by the physics itself. Okay, how that happens is, so V is equal to IR, right? So if you want to sort of multiply I times R, right, you can do that with the V. So if you have, so you can invert that and get VG is equal to I. So if you apply a voltage, pass it through conductances, the output of that conductance for a fixed value of a voltage drop will give you a summed current at the output. I mean, this is a very simple idea by using Kirchhoff's law to be able to do that. Opinion on benchmarks. How do you compare one type? Yeah, so it's very difficult to basically compare one thing to another. I mean, you have to do apple to apple comparisons, and doing that is not easy. I mean, the whole field, there's like a whole evaluation aspect of computer architecture, which basically just deals with how to evaluate things correctly. And basically one way to do that is to basically ensure that the application that you're working on is the same. You can't compare a CPU that's doing, it has 2 cores and it's doing all sorts of things with specifically a GPU. I mean, simple numbers like floating point operations per second is one thing, but I mean, I don't think that's a fair comparison here. Gaurav, your questions about neuromorphic computing. Yes, this is about neuromorphic computing. It's about machine learning, neuromorphic computing, and that's kind of one direction where things are going. Quantum computing is another direction. Neuromorphic computing is one direction. Accelerators is another direction. So yeah, that's absolutely right. In simple terms, what does GPU architecture starts differentiating from accelerators or vice versa? Man, that's a long question. I don't think I'm going to be able to answer that now. Physical devices may move from silicon to, yeah, there are so many new materials, there. See, replacing silicon is going to be a very Herculean task. I mean, the amount of man hours and effort that has gone into silicon is insane. And also silicon is basically something that has been studied so well that it is like the substrate on which everything else sits. So people are now trying to use carbon nanotube FETs that are integrated in the back end of the line. You have memristors, magnetic tunnel junctions, all kinds of interesting technologies that are being integrated into the silicon system. But so other material systems will definitely play a role, but silicon is not going anywhere. It will happen with integrated with silicon. These things will be hybrid basically. Can you tell me how to implement AI or ML in VLSI? Dude, that's like a 10-year research project. No one can tell you that in 5 minutes. That's something you have to, that's not, no one can tell you what that is. So what is getting merging of digital and analog computing as a hybrid chip? What of getting merging of, I'm not sure what you mean there. But basically you can think about that as a digital main processor that is doing your everyday normal tasks, and whenever you need to do some accelerated activity, you can offload that to an analog co-processor or a side processor that is basically going to sort of natively implement analog behavior, and that co-processor will give you all this parallel activity that you want to do, right? So basically I guess I'm not saying that well. Basically what I mean is that you're going to have co-processors that make the most of these analog computing schemes, but you are still not going to get around digital computing, right? Digital computing is still going to be the main thing that you're going to interface with. Good source for AI or ML and VLSI. So the thing is, this field is so new that I don't know of any books. You may be able to find some books online, but I think you should just go on YouTube and listen to lectures. And basically, this is a research field right now. So for this field to come into everyday mass market technology is something that will take time, right? Apple and Google and all are already doing this, but they are doing conventional digital VLSI. They are not doing, these kind of weird analog computing kind of techniques. You see what I'm saying? So I think one way to do that is to sort of understand AI and machine learning. Go look at some video lectures from Stanford or from MIT. You can find them online very easily. And if you have a background in VLSI, you should be able to combine those two ideas effectively.
Great. So I think Adit, it was a nice one. So one question which I think Shatabdi asked is about the hybrid thing. I think it was like neurology and the digital. I think she was asking about that particular part, like, okay, moving forward, maybe they're going to be a chip where the multiplication and the addition is going to be done the way you have explained, and the rest of the thing is going to be done by the digital chip, or maybe the existing one, like the way we are doing rest of the thing. Maybe she
Right. That's
maybe.
that's that's yeah, you can kind of think about it like that, as basically you have a co-processor that is going to do tasks for acceleration,
Hmm,
and all the conventional stuff is still going to be digital basically.
great.
All this, see, all the stuff at the end is kind of my opinion based on my research and the field that I'm in. This is not fact. So don't sort of treat this as fact. What will happen is what will happen. I don't know what will happen, right? But this is just sort of one direction where things may go. See what I'm saying?
Yeah, I think most of the people they are done with the questions now.
All right. All right,
All right.
Advait, thank you so much for
Yeah,
your
thank you for
valuable
this
session.
opportunity. Yeah. All
Yes,
right.
and I must say you brought a breath of fresh air with your outlook, and what a crisp session of how perfectly you encapsulated the significant aspects, and your enthusiasm was certainly coming across. Um, uh, Welcome to Expert Talk, Sampada. Are you in?
Yeah, hi, good morning. I'm in.
Morning, Sampada. So, Puneet, do we have time to go over one of the campaigns that we are running currently?
So maybe what we can do after Sampada talk, we can do
Sampada's
that.
session,
Yeah.
absolutely. All right. So, Sampada, I'm just going to take a few moments and introduce you to our attendees. Let me just um, tell briefly about what you have done and what you have achieved. Um, So Sampada Pachori is the Director and Industry Advisor at IUCEE and a founding director at Talented Unlimited India. She is multifaceted with qualities and skills that are inestimable. She's an epitome of versatility and passionately working towards educational reform for the last 4 years with or without an organizational support. She has been playing multiple roles in her more than 17 years of experience and achieved recognition in various sectors, be it industry or philanthropic work. Well, she has, as I said, 17 years in semiconductor industry. She's been working with ST Microelectronics in India and Italy, Micron Technologies Incorporated in USA, Sankalp Semiconductors, and Massam ESIS. And when we talk about her semiconductor industry experience, she has expertise around physical IP design, implementation, and verification, technology node experience of up to 7 nanometer on TSMC, UMC, and STF DSOI processes, design and development of static RAM IP libraries, standard cell libraries, CMOS image sensors for PC, and cell phone cameras, test chip, and full chip implementation. And there is a huge list. Apart from being a technologist, she has done various voluntary projects where she has served as teaching associate at Center of Inquiry, Richland District Primary School, Columbia, South Carolina. She was a Global Industry Advisory Forum member, curiosity inspired learning workshop conductor at schools, primary and middle. From the industry point of view, she conceptualized in the industry aligned training program for electronics engineering students. She has defined the business plan for skill training, did industry collaborations to lead the trained students on the job internships and placements like Indian Electronics and Semiconductor Association, IUCEE, Indo-Universal Collaboration for Engineering Education, IEEE, ITTC, Indian Test Technology Technical Council, etc. There is so much more we wanted to mention in your introduction, but due to the limited time, we could only list a few. We want to say that you are truly, truly an inspiration and an extraordinary human. All right, over to you, Sampada.
Thank you. Oh my God, Prerna. I don't know if you were talking about me or someone else. That sounds like really a lot. I think I wrote it, and I think I'm the one who sent it to you. But hearing it back makes me feel a bit surprised at myself. Thank you, Prerna. Thank you, Puneet, for giving me this opportunity to talk to everybody and share some of the learnings over the 20 years that I have developed. So it's 11:17 right now. Before I begin, I will want to know how much time do I have? I kind of prepared for a 45-minute presentation, but
Yeah.
do I have to rush or do I have to?
No. So take your time. Just do it in a whatever the time you have.
Okay, all right. So I'm just going to share my screen. I'm assuming my screen is visible to everybody and I'm audible to everybody.
Yes.
So my topic is, what's the big deal about industry skills? What is the big deal about industry skills? Can I get the poll now? The first poll?
Yes, you can do. I can do that. You have to just give me 1 second. Okay. Give me some time. Yeah. So you need a poll one. Am I right?
Yeah, the poll one.
Okay. So guys, so those who are live, just attend this poll.
Wow. That's interesting. Okay. So it's interesting that I noticed 64 or above 60% people did not really notice the spelling mistake, while about 30 to 40% were able to spot the mistake. I'm not going to be judgmental about it with anybody. It's just throwing a point at how the brain functions and how we are conditioned and tuned. So I think I have fair enough data which is staying consistent for the last 20 seconds. I'm going to end the poll. But yeah, thank you. I'll remove this poll now. So let's see what we have. So it all begins in kindergarten, isn't it, for us, when we get into the educational system and we are given books which show us, what is it about objects. So we learn about colors, we learn about different objects which surround us, the world that we are living in, and we are told all about the what and the why of the things. We learn all about the science of how things move, how things function, how things are built around us. But you must have noticed, I mean, as we grow into the school system, we begin to identify some teachers as good teachers, and some of them we call as, not so good teachers. What is it that differentiates a good teacher from a bad teacher? I mean, is it that we are saying the bad teacher did not do her subject very well? Not really. I mean, they're all coming from the same education system. They've all read the same books. They all have the same technical background to what they are teaching. It's just that their ability to deliver the information to us is what makes them good or bad. Let's look at one more point. This is about race across America. This is one of the toughest race that happens in cycling. It happens in US. It starts from one end of the coast, west coast, and goes all the way to the east coast. It's a test of endurance, physical and mental both. And it's very tough to say whether it's physically more demanding or mentally more demanding. For people who participate in this race, it takes a lot of planning, preparation, coaching, strength training, conditioning their body and mind, and creating a team to even make it to the start line of this race. And whether they'll be able to finish it, there is no guarantee, despite the humongous preparation that they go through, and they make the best of their team as their crew. And how they make it to the finish line, whether they drag themselves to the finish line or whether they do it with the kind of performance that they desire, that's where the marriage of knowledge or competency and execution or skill comes into the picture. How well they finish, that's the demonstration of skill and knowledge combined together. So I think we made a good point to say knowledge and skill go hand in hand. Knowledge can bring you to the start line, but it's the skill which takes you to the finish line and maybe even beyond that. Back in 1968, L.G. Peter, he's one of the great names in business, made a statement, and that's, mind you friends, coming 50 years ago. He says, advancement in a position for any individual, as far as their performance is concerned, is based on their previous role, not their performance in the current role. So it's basically most of the times, and not most of the time, I can safely say 100% of the time, it's our technical competency which may land us into a job or a role that we are going to be working upon, but we don't really know how to do that job as well as we are supposed to be. Our soft skills are hugely responsible to bring out our technical capabilities and competency to perform in that job role, right? And in any organization, people who are able to bring forth their collaboration skills, their conflict management skills, their ability to prioritize their tasks are the ones who are the effective employees to that company. The remaining become a huge cost. They can actually create an exponential damage worth to that industry or the organization where they're working. Let's see it even better. In most of the companies, when they are being struck with economical challenges or they are running loss in their revenues, they start thinking of cutting costs, and in cutting costs, they start laying off people, right? Firing happens really quickly. Now, when a firing is happening, what is it that makes a person stay or being fired with a lot of difficulty and thought? I mean, people who are sound technically, as well as people who are not so sound but are demonstrating good attitude, have an ability to learn. That's where the battle comes to rest. But anyway, I don't want to go into that. That's a particular organization's choice and agenda based on which they decide. But it is definitely put on the table at the time. Now, for an average workplace, how do things look like? Wherever the productivity is not so good, what are the indicators? Basically, these are people who are stressed out. They're working longer. They're not working smarter or efficiently. They're not able to produce as much as they are expected to, and they also feel demotivated and not fully rewarded or recognized. There are also situations in such organizations where they do not know how to handle conflicts, or they try to avoid handling conflicts. And all in all, this poor communication causes a lot of loss of productivity. And the third and the most important, where they're interfacing with outside the world of their company, is they do not come up as great brand ambassadors, and they're not able to suitably represent the business value, and hence they can end up bringing loss to the company. So we're talking of communication skills primarily, and which becomes one of the most common deterrents in productivity in a company. Some of the things which happen when we are talking of productivity. So a lot of meetings happen. I'm sure people who are working right now, or even those who are in work right now in colleges but are conducting meetings for whatever they do, would agree with me. When we get into a meeting, we spend 1 hour. So it's something, every meeting is naturally assumed to be 1 hour long. Now, whether or not there is something worthy of an hour's discussion, people like to take 1 hour to discuss that. Do we really always need a meeting which is going to take 60 minutes? Or can something be done in 10 minutes or 12 minutes or maybe 30 minutes and not really, spending 1 hour on that? So we do not give importance to that. Just hold on a. So we do not really understand the value of how much time we are spending in a meeting. I mean, we are bringing a group of 6, 7, 8 people in a conference room to discuss an agenda, and we assume that it's 1 hour or it's 30 minutes that will take for this agenda. The other thing is lack of trust between people, lack of credibility in what the other person is telling you. So we again, when we are listening, we do not completely focus on the point. We are always quoting it with the impression of the person from whom the point is coming. And then, of course, if there is no moderator to that meeting, there is a lack of focus, there is a lack of direction to converge onto these points. So these, in long run, affect and impact the company's performance hugely. And let's see how much of that impact means in terms of dollars. So there was one report which comes from Skip Weissman. It's a consultancy firm, and they mentioned that around 5,200 US dollars are spent per year per employee, or rather lost per year per employee due to bad communication or poor communication. And if you see some of the data, which I don't know to read out each and everything, but 63% of people consider quitting their jobs because of poor communication. And imagine these 63% people are the ones in whom the company has invested heavily into. 53% say that the companies do not communicate with them properly or do not encourage them the way they would want to. And around 60% have a grudge against their CEO because of the communication mismatches or gaps that they notice. I cannot really give you a course on good communication here, but I can point out some of the basic etiquettes which go a long way. Even if we don't go through a workshop on communication skills, this is something which is pretty obvious, but needs to be reminded every now and then. For everything that we do, including the fact that right now I'm talking to you and making a communication, the why should be clear. Why am I communicating with you? Why am I telling you all of this? Who am I telling to, right? If it is a verbal communication in an industry, typically it makes sense to have a documented log of that, because when it is being communicated, there may be a certain situation or a context. It's only going to change every time you go back and refer to it. Also, communication should be properly established in a calendar. You cannot walk past an employee and as you walk by, you casually say, okay, do this. Or did you look at the mail that I sent you? Or am I'm expecting you to come back to me with a report on something? That's not really the right way to communicate a message or give an instruction or expect a report. All these communications which are of business relevance need to be done properly with a structured instruction going back and forth. Being a good listener, I think this is something everybody would emphasize, and it's the smallest phrase that I can give, and it's hugely misunderstood. It takes a life time of devotion to really be a good listener. And I'm still learning to be a good listener. And what it means here is that you're not listening as you're listening as the person who's talking to you. And that takes a lot of practice and patience and a lot of other qualities, which we will speak in a few minutes from now. Of course, it is important to alter your message or note or tone or language based on the audience or the recipients who you are referring to. Brevity, it's again something which is most ignored. We have a tendency to not know our language well or not really give enough importance to the language. If we are using Hindi or English to communicate in a workplace, we think that we should only shine up as a great BTech or an MTech with great grades in my science and maths, and English doesn't matter. Well, your grades may not really make you a fluent speaker, but your command on your language is very important in a workplace, because you can be a great engineer, but if you do not know how to express your point in the most appropriate vocabulary that is picked up and chosen, you may not really make much sense, and you may lose attention of the people who are listening to you. And please stop getting into the habit of repeating your sentences. We also need to develop enough confidence that when we are speaking to somebody, and especially if it requires us to dominate our point over somebody else or mention something that may impose a conflicting situation, we are assertive, we are firm, but we are polite, because it's not the individual that we are referring to, it's the point that we are putting across. And of course, non-verbal communication or body language is absolutely the breaker for any message that goes across. This model NEAR was actually developed recently by Gartner, and I believe this refers a lot into the pandemic situation that we are faced with. And it's not only for pandemic, it's going to be the order of the day as we see in most workplaces. And the NEAR model here is number one, N is for normalized self-direction, where we are looking into a system where managers are no longer our supervisors or directors or dictators to us, but they are more as a coach. They are holding our hand with lot of trust, and they are telling us how to do things and what is to be done. They are more focused on the output, and they give us enough faith to bring in our own process as long as we are able to deliver the output which is intended. And that also means that the responsibility lies on every employee, every staff, that we are self-directed, because now we are no longer sitting in a company office space where we are constantly being watched and there are CCTV cameras noticing how many times I went up to go for a coffee break or for a washroom break. So this is more about being self-directed and being in good faith with my supervisor. This also means that the new form of relationships will be formed between colleagues as well as between seniors and juniors, where they are able to keep a close watch through a remote virtual platform, not being in a enclosed office space, onto what's going on in the employee's life and whether there is a good possibility of requiring an intervention, or if the person is emotionally stressed, or if there are social interruptions. Uh, those new relationships will be establishing a new kind of culture between people working in the same office. Accentuating the positives. So earlier, since we were talking face to face, it was much more prompt for a boss to call upon his junior and tell what went wrong, or what was it which was not as per the expectations, or what was delayed, or what was a disaster. But since we are talking more and more of culture where people will be working from wherever they are, to keep the faith and trust alive and to nurture it, it is more important that every feedback is not only fact based, but is also laced as much with positive feedback, which is genuine positive and genuine negative. We cannot simply ignore the positive feedbacks. The last and the most important here is revamping the team expectations. We cannot take our team for granted. We cannot give them a casual task and then maybe give an overlapping task to another person, because now we are not sitting in the same room. We are not really watching what these two people are doing. They may be working at their own pace and in their own time windows, and we may end up losing a lot of company hours if we do not define the expectations from multiple people in the team together. So these are all various skills which get demonstrated in a workplace between a junior and a senior. These are some of the ethical behaviors which are going to establish a good functioning of the skills which I just spoke in the last 10-15 minutes, right? So this is not something separate. This is very much ingrained and underlying everything that we do or say. Honesty. So I must tell you one of the conversations I had with one of my ex-employers, and I asked him after I received my offer letter and I gave a yes, and I had my first meeting, and he was the CEO of the company, and I was having a first meeting with him after joining. And I asked him, what are your expectations from me? And he gave me just one word, which is, he said, be honest to yourself. And friends, that's very important. If I'm honest to myself, it's automatically guaranteeing everything else. Everything else falls into the place. I cannot be cheating with myself. If I'm honest with myself, everything that I do will have a value, will have a sense of perfectionism coming out of it. And of course, that also means being integral with the people that we work with, being truthful to our words. Fact-based decision making is something which again cuts across many things. You know, we're talking of technology, we're talking of soft skills, we're talking of interpersonal behavior, we are talking of human machine behavior and interfaces. Unless things are fact-based, they don't really go through, they don't pass through, they keep changing. So you must have all heard of Chinese whisper, right? So if you're basing any instruction or any communication more on a very subjective phenomena, and if it is not backed by facts, like a Chinese whisper, it will keep changing as it gets passed on. So fact-based decision making comes not only handy, it's actually important and essential. Accountability, again, I think I don't need to explain literally the meaning of accountability or responsive behavior. Compassion and empathy is important because that is what makes us a good listener. That is what brings the elements of trust and faith and good qualities and good interpersonal relationship between people come into the picture. And it's not something that can just come in, or you can go and take a sign up for a workshop and then come back and say, okay, fine, now I'm certified compassionate, or I'm certified empathetic listener. It doesn't work like that, friends. It basically comes with practice of being a good individual, and it reflects not only in your workplace but everywhere around you in your personal and professional life. In a business, it becomes a very tricky situation where business targets need to be balanced between emotional intelligence and financial intelligence, if I could use that word. And that is where a good business owner or a leader makes different decisions. And we have names like Tata and Azim Premji, who we always take with a lot of regard because we know they have mastered the art of this balance. Now let's look at some of the facts which were put in by World Economic Forum, and some of the new skills which are the talk of the town. The topmost here is learnability. And I'll just mention these skills here, but over the next 2 or 3 slides, it will become clearer what I mean by them. Troubleshooting and problem solving. In fact, this was one of the skills which I learned pretty early on, where I had the ability to look at problems, but I would always struggle to narrow down on a solution because as a perfectionist, I always thought I needed to have a verified solution. I needed to have one solution. I needed to have a solution which was foolproof. So I was always struggling to be a problem solver, and I always went on, and many times I would take a lot of time to turn over my project because I could never converge on a solution. It took me a while to understand there is not necessarily a single solution to anything. A solution must be there. It needs to accompany the problem, and it's always surrounding the problem. The longer you spend time in understanding the problem, the solution emerges right from there, from the core of the problem. And then I also understood that giving one solution at a time is not the end of it. You can come back with a refined version of a solution, or you can come back with multiple variations of a solution, and it's still all okay. So this was a skill which I developed over a period of time, especially in the early years. The bottom two are again more focused on the current times and the times ahead. Interdisciplinary, I think it goes without saying, we are no longer looking at mechanicals and core engineering disciplines, right? Mechanicals and electronics, electrical and all. We know that most of the development of technology around us is cutting across multiple core engineering disciplines. So while it is important for us to stay very truthful and go deep down fundamentally into one of the core disciplines that we are working upon, but we need to be very alert, watchful, and adaptive to the surrounding technology, which is essential to bring out a product. We may not necessarily acquire 3 degrees to become interdisciplinary. No. This is not what I mean. we may still stay with 1 or 2 degrees maybe, or if you think you are really committed, you can go for for 3 degrees simultaneously, but that's not what it means. Not everybody has to do that. What it means is that you have the ability and the sight and the knowledge of what's happening in the other domains and how to connect with what's the new technology asking for. Multidisciplinary, how is multidisciplinary different from interdisciplinary? So I'm sorry, pardon the spelling mistake here again. So no, this was unintentional. The spelling mistake I put in the beginning was purely intentional. So I am an example of holding multiple careers. In fact, Prerna was trying to speak out just that. So while I started off as a VLSI design engineer, and I spent clearly 14 years being a hardcore technical developer in SD and Micron and a few other companies, I eventually grew more into management and looking after people and resources. And how that happened also has a root in my first 14 years. So while I was working with one division, I had my eyes and ears open to the multiple subdivisions. So if we were working on memory design, I never shied away in doing the physical implementation myself. So I would do the schematic design, I would do the memory characterization, I would do the layout. I was never restricting myself to see this is good, bad job, this is bad job, this is prestigious job, that is not so prestigious job, although it exists so deeply in the industry, but I kind of stayed away from that and I did not shy away from it. So I had a very good background all the way up to full chip design and verification. And that's only because I was open. I was always hungry. So I was able to see what happened. And I was fortunate to be in Italy, in Catania, next to the processes, where I could also understand how the models were being developed for a technology. So this wide view made me better and better with the design for manufacturing skills, which I could come back and demonstrate every time I did my next project. So that's one way of multidisciplinary and interdisciplinary, right? The other thing is I did not hold myself to only VLSI design, right? I could actually see myself coming back and giving it to the next generation of engineers who were coming in. I enjoyed mentoring them. I enjoyed training them. I enjoyed making them ready for the job, which is how the gradual shift into education took place for me. And I became more and more involved with the course content development. And today, I'm kind of launching a new program, which is a great uh, embodiment of multiple gaps which were observed at different stages in the whole life cycle, which I'm trying to answer. And because I've been able to see them with my own eyes and perceive the damage they do, I'm able to create a model which I can safely say is foolproof. So that is what I mean by multidisciplinary. And all of this happened because I have the ability to learn. And I'm not really marketing myself here. I'm only using my example to make a point, right? I'm sure there are people, many people who are way better than this. It's just that it's easy for me to explain from my own life example. Let's look at something even more important now. There is a shift in industry skills happening. So if you think that I'm kind of going on in the circle of mentioning the same skills which people have been talking for the last 20 years, good communication, leadership, teamwork, all that, these are all very common words. What is it that I'm bringing out new? And that's not really my job to bring out something new to you, but my job is to give you the right focus for the next 10 years, which is where the digitalization, the industry 4.0 is causing a shift in the expected industry skills. So of course, there may be a bucket of industry skills, but which skill goes up and which skill goes down, or which takes prominence or dominates is what I'm trying to say here. This is a data from McKinsey. And if you notice, there is a expected rise in skills of higher cognition, social and emotional, and technological skills. And more and more of physical and manual skills will get, fully absorbed within the automation. That does not mean that people who were doing physical skills will become jobless. It's rather, a view for them to understand that they have to advance themselves from not just staying in physical and manual, or not just sticking around with basic cognitive skills, but advancing themselves in the skills so that they can stay employed, but in a different role altogether. What are the drivers of this shift? Of course, digitalization is the drivers, but five things you may notice here, and I'll start from globalization first. We're becoming closer and closer, right? That's what globalization is doing. Another thing which globalization is doing now is we're moving away from competitive world to a very collaborative world. And you must have already seen that come up in the way the entire world united to fight against corona. Nobody's saying, okay, this is my vaccine, this is my drug, this is my country, this is my health system, and I will not be sharing it with you. People are realizing that my health is as good as my neighbor's health. My neighbor has to be safe so that I'm safe. What I'm doing, if it is benefiting me, it should be benefiting the other person. If there is a technology advancement in my area of research, it has to benefit the rest of the population as well. So this is where a very collaborative, fast-paced, of course, because technology now changes at the blink of an eye, and very, very relevant innovation. Nobody cares for things which have been told before. Unless you bring a new indigenous value to your innovation, it's just another term which everybody is running after. And of course, great constraints, because people are becoming, as I said, fast paced, right? So the constraints of globalization and time as in, how fast things are done, are putting more and more stress on relevant innovations. Mobility, that's another thing which has gotten highlighted due to corona. People have understood telecommuting is not just a fad or a fancy, it's a reality. I mean, I have to tell you, back in 1999, when I was in Italy, my boss, he was a wonderful guy and very fun loving. So in Italy, typically August is a time when most people go for a month-long vacation with their families. And he also was family oriented, but at the same time he had the responsibility of getting the work done. So he would go with his work and laptop, and from the beach he used to fire simulations. And I'm talking 1999, and we are doing that now, telecommuting. Of course, all of this demonstrates a lot of self-discipline, a lot of ownership of what we are trying to do, our own time management he has to do, otherwise his wife will simply just throw him in the ocean and never bring him back. So he has to demonstrate that level of management where he can do a good multitasking of satisfying his family needs with his work needs. Jokes apart, this is the new millennial workforce which we are talking of, and we have stronger attitudes. People don't just listen to you because you are superior to them and you're telling them something. There has to be a backed reason which is backing your statement. People have higher expectations. People have more refined ways of working, many ways of working. Interpersonal skills have actually reached another level. It's no longer that you say something bad and then you go back and say sorry and things can be, completely forgotten. So people have evolved into a different understanding of the human beings and each other's personalities, and you have to understand how to work around them. You cannot simply say, okay, I don't like this box, so I'm going to walk away, or I don't like this team, so I'm not going to work with this team in my next project. It doesn't really work that way, friends. If this is how it's going to be for you, trust me, you will end up alone. Most likely your boss will not put you in any good project next time round. You have to understand and detach the humans from the tasks, and develop the ability to work with a variety of people so that you can succeed and prosper and focus on the work rather than the people. We are dealing with a lot of new technologies. Things are becoming digital. Take that to your advantage. I mean, we're no longer talking of situations where a man was just dealing with another man or a human. We are looking at a much stronger man-machine interface. So expectations of my ability are not just that I say something and I assume that the other person will understand what I've said. For when you're interacting with a machine, you have to be very clear of the instruction that you do. I mean, that's exactly what coders do. They write algorithms. So they learn how to articulate their thought. They learn how to plan the processing steps in their mind and on their paper before they're able to make it into a code, because you're no longer leaving things to assumptions, right? A machine will not assume what you were trying to say. Of course, behavior here is that people have become socially different. So, I mean, how my work is being perceived, or how I demonstrate my ability, my competency, and my skill is also now being reflected not only within the work environment and the people with whom I'm working, but in a much larger social setup. So these are all the factors which are driving the shift of the skills. We are expecting 26% increase in these three skills as given by McKinsey. I probably will not go through reading and explaining each one of them, because you probably understand what higher cognitive here means. I may just focus on one of the thing, which is about complex information. Here, when I say higher cognitive and I say complex information processing or interpretation, what we're trying to say here is not everybody needs to be the master of everything. I don't have to become a super duper human brain working on complex data processing all the time, because there is too much data overload right now, and not every individual is supposed to process every bit of data which is surrounding us. What we're trying to say here is learn how to collaborate and delegate. That's what it means, right? Similarly, we look at leadership. We'll look at leadership in the next slide, or we look at adaptability, where we are able to change ourselves into the new order, which keeps coming much faster. We look at technology skills. Yes, you all are already working hard at that. Analytical skills are important. You can engage in problem solving through brain puzzles, brain teasers, and that will help you with development of your stronger analytical skills. Advanced communication, I already spoke to you about. So we'll look at leadership in the next slide. And before we do that, most of you must have watched this movie, and if not, at least heard about this movie. There was a nice concept which this movie demonstrated, and business world captured that. So what is it? You know, this movie demonstrates several aspects. It shows collaboration, it shows teamwork, it shows elements of leadership, elements of project management, and it shows many other aspects like motivational, negotiation skills, and few others. So we need to learn from this. Number one, for all of us, there has to be a purpose for whatever I do in my daily task or in my monthly or in my annual task. I need to have exceptional goals, which is what motivates me. Any average goal will never motivate me, right? For example, I can say for me, I'm also a cyclist. I can say if I have been able to ride 40-50 kilometers on a particular weekend, and if I say, okay, tomorrow I'm going to be riding or cycling 200 kilometers, that's an exceptional goal. Or if I say I'm going to be cycling 600 kilometers in a week from now, that's an exceptional goal. You know, that gives me a purpose, you know, that drives me. Personalities. So for a team, let us not focus on what a particular member is not capable of doing. This person's weakness is for him or her to work upon. But when I'm forming a team, I have to be very, very mindful of the strength which each team member brings. And I kind of create a camaraderie of those team members, which is built up on their strengths, right? And then I use that to promote. So how do I actually go about it? So I kind of form a team which is based on their strengths, their abilities. I kind of help them develop a camaraderie between themselves. And I leave them together to really fight with each other. Which when I say fight, it's more, more of trying to adapt to each other. They may be all bringing their own insanities and their own different personalities. Let them learn to grow with each other and accept each other as the other person in the same team. And then we define the norms of working, the actual task allocation. This is what we are all supposed to be doing. This is our common project mission. This is our deadline. This is our performance expectation. And we basically go to this level of norm definition. And finally, we say, okay, here we are, ready to go and perform. And of course, when we say persistence, it's on every person in this team that they put in their best. And all these factors were clearly highlighted in this movie, which is why I brought the reference. So this is what you see. This is just a reflection of what this movie demonstrated in a way. Now, this is one last skill variation that I'm going to talk about, because this is picking up very much. And I, again, am a living example of being a freelancer or contributing to the gig economy. So we are going to be more and more of people who work as freelancers. And freelancer does not mean that today you go and say, okay, boss, I don't like you. I don't like this company. I'm going to turn in my resignation, and from tomorrow I'm a free bird. That's not really what it means. Eventually, that is what it means. But to become a freelancer, you have to first work upon yourself. So what are the skills which a typical freelancer should have to survive? So, I mean, if you're able to, focus on these things listed here, you will succeed as a freelancer, and you may do much, much better than simply being employed, right? So number one is that you are making a career which is based on problems, and not just because there is a job role which has been given to you. So you're not driven by JDs anymore. It's a very different mindset, right? You look at a problem, you look at a challenge, and you take it as an opportunity to work upon. That's how a freelancer mind works. You're, of course, you're self-directed. I've already spoken enough about it. And you take ownership of your successes and failures. If you want to call them failures, I rather like to call them learnings. And I have to tell each one of you that we have to stop using the word failure as much as possible and replace it with learnings. It kind of gives a lot of positive corroboration to the fact. It also means that I am now responsible for hiring my own team or acquiring my team. I may or may not hire a team. I may actually develop a group of people who will work or share the mission, but they may also be employed elsewhere, or they may all be freelancers. But a group of freelancers can come together for a particular problem solving because it is common to them, right? And you have to be very particular of how you create this team, because there is no hierarchy, there is no boss, there is no system where you can go and complain, okay, this person is not doing the job right. No, you are owning the entire operation, right? And the person who comes and joins you could be senior or junior to you, age wise or otherwise, but here you're working more as a team at the same level, right? Working out loud here, this basically means that you are taking care of all the learnings of this work, and you are keeping a good log of everything that comes to your mind or that gets generated, and you use that to define the next work that you're going to take up. Asking good questions, this is one of the quotes which came from Einstein, which said that if I had a problem and if I was given an hour, I would spend 55 minutes to understand the problem. So asking good questions is basically, you could be asking these questions to yourself, or this could mean the research that you do yourself to understand what the problem is. So if you spend 55 minutes in that, it will take you only 5 minutes to really come up with a solution. The solution emerges. I already spoke to you before. Agile learning here means that you have the acceptance that you will keep learning and growing your skills around the work that you do. And if there is a new work which comes to you, which partially overlaps your current skills and competency, but you have the drive and the learnability, you take it upon yourself as the next challenge. And in the process, you become better and you learn more. Hustling here basically means that you're not only executing the work, but you're also simultaneously playing the role of a salesman or a marketing man and trying to get more and more work from that, and which requires a lot of self-promotion and branding. And friends, these are all the skills which are not going to just make you a good freelancer, but if you have these skills, you will do way better in your employment wherever you are, at any stage or level you are now, or even 10, 20 years from now. So let's see, how much time do I have? If I have time, I'll play this 2 minutes video. If not, then I'm going to close. So I'll just go to the last slide. So Prerna, Puneet, do I have 2 minutes?
Yeah. So
yes.
you have.
Okay, so I'll play this video. It's obviously it's not mine, but it's something interesting and sums up everything that I've spoken. So let me play that. I had to stop sharing because it's on YouTube, so I have to start sharing the other screen.
Sure.
You can see the screen now?
Yes, we can see screen.
So that was the video that I shared, and I hope everybody could see it and hear it.
Yeah, I think.
The future of jobs and skills is one of the most important in education. A student entering formal education today will be making decisions about their career by the year 2030. But wait, we already know about the future of jobs.
Were you able to see the right slide now?
Not right till now.
Is it visible now?
Yes, now we can see.
Okay, so I'm kind of done with my presentation. The concluding slide is right here. So who is responsible for my skill development? And at this point, I will also request you to bring the next poll, the last poll. And I leave this question for people who are attending this to answer for themselves. In case they need help, they can maybe start out with reading this book by Stephen Covey. Not saying this is the first book anybody should read, but maybe this is a good start. It kind of puts you on the right tracks to look at yourself and work on polishing who you are and how you are. So thank you for listening to me, but please answer these questions in the poll. I would like to see from each one of you, what are your views on these 4 questions which are there on the screen for you right now. Nice trend. Looks like I was successful in making a point or driving the point across.
Excellent indeed.
Any questions for me?
I see one on the chat window. If I can read that out for you, Sampada.
Yeah, please.
Okay. I think this question is from Senthil. If our goals are ambitious, won't they be burnt out eventually?
So how do you really define goals which are ambitious, right? I mean, the fire to work on your goals is an endless energy which comes from within. And a person who works on his own goal does not really see it as ambitious, less ambitious, or over ambitious. For that person, it is the goal, it is the aim, it is the purpose. And it brings with itself a strong sense of achievement when he's working on that goal. And there is no place for burning out, because the fire that burns within becomes stronger and stronger as the goal becomes close, comes closer and closer. And in fact, many times you would notice the goal itself will become larger and will take on a bigger shape, or it will lead to another new goal or another new milestone. So it is an unsatisfied hunger which pushes the person. And so there is no real question of burning out. And if there is a burnout, which that means it is not your personal goal, you're basically trying to work on somebody else's goal.
Right. Perfect. Great. Great. Thank you. Thank you, Sampada. What an insightful session. You were flawless in the speech, and I personally thoroughly enjoyed the session. The aspects you pointed out were very informative and valuable for our young attendees. Sheer honor to have had the pleasure of listening to you.
Thank you. And if there are any questions which I can see if coming, I'll be happy to answer them later. I know it's 12 past 12. I don't want to hold the third speaker waiting. I'll be happy to answer questions for people otherwise.
So there is one let me just read that out. Sampada, it's from Abhi Rohila. When a person is super motivated and ambitious, family time is gone. How to balance both?
Yeah, that is right. So, family time and work time can definitely put a lot of challenge when somebody is overly driven with an objective. And it is again up to that person to bring the balance. So, for example, I'll use my own case. I have a family where most of the people who demand me are late risers. They like to sleep late and they like to get up late. So I found a way to arrange my working hours, especially which require a lot of thinking and which require me to invest myself uninterrupted in my morning hours, because I'm an early morning riser. and it doesn't really conflict with them. So the solution to this managing and balancing also comes from within your own setup. You have to watch out how do you keep the other person satisfied, at the same time keep your passion alive. But one thing, please always remember, again, coming from an experience, especially being a woman, this is particularly more and more true for a woman who is into a family setup. It is easier said than done. It does put a lot of stress, and I have to find my own way of taking a break, whether it is on a daily basis or whether it's on a once a week kind of a basis. So it's walking a knife's edge at all times, particularly if it is a woman, वो भी Indian context में. So it's not easy, my friend, but it's possible. I'm a living example of that.
Thanks, Ampada. So I just want to add one more thing, because people are just this particular question is like next to me also. So guys, I just want to add only one thing. So right now, if you're comparing your work with someone else's work, okay. So let's put in that particular way, because a lot of people have this confusion and they always talk about the work-life balance. They always talk about the family time. Whenever I have had discussion with someone like, okay, why can't you just do something which uh, uh, like motivate you, or this your work, and they always talk about the same thing. So think about like, okay, if you're working for someone and they are pushing you and they are giving you the salary at the end of the month, and I'm 100% sure you will work for them day and night. And at that particular time, even if it is it's just creating a problem with the work-life balance, you will still work because you're getting a salary at the end of the day. But when the things come like, okay, you have to work for yourself, so then we start thinking about the work-life balance. So just put yourself in that particular situation, like you're working for yourself and you're pushing yourself, and then you have a flexibility to manage the different things also. But in case if you're working for someone else and they are pushing you, you don't have that flexibility, like, okay, when to manage, how to manage, and what is the deadline, and all of the things. Someone else is deciding all these things for you. So it's just like Sampada was saying, same thing I was say, like, okay, it depends, like, okay, if you're passionate, if you think, if you like that particular work, if you're doing something which is something like you wanted to do, I think everything will come automatically. Early, you can just wake up early, you can just do it at that particular time, you can spend the time with the family also, then in the late night also you can work out. So you can do in that particular way. But if you're in that particular zone, like, okay, uh, passionate means and just having something for ourselves means like we will work for 24 cross 7. No, you cannot do 24 cross 7, because you're going to be have only 24 cross 7, that's all. So you cannot work for that particular
I want to say something here. I know I'm eating into somebody's time, but I think this is important, and I
yeah,
pray
sure.
that you forgive me for that. Um, Friends, my career actually saw several breaks precisely because of this balancing between family and professional life is concerned. I actually took one break when I had a serious medical condition, and I knew it was important for me to get better, and I gave my resignation. The second, and it was very serious, you bet. The second time I took a break, it was for 6.5 years, and that was a time when I had just given birth to my babies. And 6.5 years, it was my conviction that I wanted to raise my babies and not let a maid or anybody else bring them up. It was a choice that I made. It's all a matter of choice. At every point of time, in any situations you are faced with, whether it is inside a workplace with a colleague or in your house with a family member or a situation in your life, it's a matter of choice. And I made a choice that I gave up my career for good, forever. For 6.5 years, I was not working. And then again, I made a choice that I have to wean off of being a full time mother, and start to find a space for myself and reclaim my professional identity. And I started working on it gradually, few hours at first. And it took me 4 years to re-establish myself with a different role, with a different skill set, with a different idea altogether. And those 6.5 years when I was not working at all, I was reading a lot on psychology. It was not planned, it just happened. And just because I was reading all on psychology, I do not have a degree in psychology, but that helped me understand and become better as an individual, not only within family, but also I could use that. I mean, anything that I do today is hugely driven by what I did then, right? Whatever I was reading then. So I was not afraid of taking a break. I'm not advocating that everybody should take a break. I'm not at all making a statement. I'm only saying it's a choice we make. And then next time we are faced with another situation, it's time for another choice. Okay. So be wise, be alert, make a choice, own it, own your choice. There is no place for repentance later on. Own your choice and walk on it. Thank you.
Very rightly said, Sampada. Um, Again, sheer honor, and you are definitely an epitome of excellence, and you are a great orator.
Thank you.
Thank you. It was truly a pleasure
Thank
listening to you. Right. So moving on to our next expert. Before that, do I have Puneet? Do I have the permission to go over our campaign just for 5
Yes,
minutes?
yes, I think 2 minutes. That's very important. So everyone should know about that particular campaign. So just give 2 minutes or 5 minutes. Yeah. Just
Okay. Are you? Can I share my screen?
okay. You want me to share? Okay.
Oh, yeah. Or you can go ahead. You also have the access.
So you just share. I think I have to just search the content.
Oh, okay. Okay. No problem. Let me just quickly share the screen. Okay. Can you see my screen? Puneet?
Yes, we can see.
Okay, perfect. All right, so we'll just take a couple of minutes to go over this quickly. This is one of the initiatives that we are running currently. This is called as Gift of Bundle. It's one of the initiatives that we have rolled in. It's been a while, and Puneet and me, we've been sharing the posters, the posts on various LinkedIn platforms. So I'm just assuming that some of you might be aware of it. So let me just dive into the concept behind this, just quickly, briefly. It's called Gift of Bundle. So that, as a name suggests, it's basically gifting a bundle of knowledge, and it is designed to help deserving students and aspirants, especially the ones impacted by COVID-19. And we are offering a huge learning package to aspirants in order to support skill building opportunities. So what does it offer? So this bundle offers 7 courses, as you can see. So currently, there are only 7 courses, but new courses over the next 2 years will be added to this bundle. So you will have the accessibility for 10 years and upgradability. Upgradability meaning that you would have free upgrades for 2 years. So some of the sessions have video lessons. Some have, a couple of them have both video lessons and test papers. So you would go through it as in when you would, purchase these bundles. Okay, so let's go on to the next one. So highlights, gift of bundle, community initiative. Let's see. It is a community initiative, and we want maximum number of people to benefit from it. We look at it as non-profit initiative, as the total revenue will go into developing new courses, and some part of the funds will be utilized in developing courses through those professionals who lost their jobs. So one way or the other, every penny would be efficiently spent on e-learning. Accessibility and upgradability, I already explained to you. So you will have access to these courses for 10 years, and in over the next 2 years, whichever new courses that we would introduce to the learning platform, the online platform, they would keep adding on to this bundle. And there are a couple of them already in the pipeline, one of which is physical design. Right. So community, I'll come back to sponsorship to donate in a couple of moments. Let's go on to the other, one of the other highlights that I want to talk about. That's community building. It's basically, the fact that it is this whole bundle is affordable, upgradable. We're kind of building community. Let's look at it this way: either you buy it for your skill building, or you're gifting it to someone in need. End of the day, you're spreading knowledge. Skill building and development. Well, we know that markets are soaring, innovations are happening, industries are adhering to modern techniques. We have to keep ourselves updated, and e-learning content would always turn out to be your best friend, making sure you're constantly aware of the industry changes and advancements. So always learn and never stagnate. I got this line from the video that Sampada shared. I just love this line. Always learn and never stagnate. It's very inspirational, right? And e-learning reinforcement, very simple as the name suggests. We are basically reinforcing not just e-learning, the learning. So either you learn from e-learning content, or just simply learn. We're just trying to reinforce the fact that you guys keep learning, never stop. Don't cease learning. Just keep collecting information from every source possible, right? So about one of the highlights that I said that I'm going to talk about, so sponsorship to donate. ExpertTalk is the company that came forward and rolled in a test that is on October 3rd, 2020, and so basically it's their selection criteria, and completely on the merit base, 2 candidates would be able to avail those bundles for free. All right. Is there anything else that Puneet, you would like to add to it?
So, Prerna, I'm good. Just to summarize what Prerna just highlighted, it's just like what we are doing. We are running a campaign, and in that particular campaign, if any one of you want to help someone, so if you know those people, and if you just want to gift this particular bundle, you can just gift this bundle. So the cost of this bundle right now is just a 10,000, but if I will say the worth of this particular bundle, even the right now it is almost like 30,000. And the way the way Prerna explained, there are a lot of courses which is worth I would say in the next 2 or 3 months is going to be like almost like 50,000 more courses worth of 50,000 that courses we are going to add there. So like physical design. So the current batch physical design, that itself is a you can understand like we took almost like the tool and everything is like more than 50,000, but that's we are going to add it there. So all the recorded sessions, the papers and everything going to be there, and is going to be there for the next 2 years. That means in the next 2 year, whatever the courses we are going to develop is going to be the part of this bundle. And like whosoever is going to gift, so whatever you're going to gift, like if you're gifting just a 10,000 rupees, that's going to be there for the is there. So pricing is there, nothing going to be increased. And we are planning to add almost like 50 new courses in the next 2 years, and those courses are going to be developed by industry experts. That's the thing. Or some portion of that particular courses we are going to develop through the people who lost the job. So that doesn't mean like only on the fresher side, but there are people, they have like 5-6 year of experience and they lost their job. So I know a lot of people, they are good in their field, but just because of certain reorganization or all those things, they lost their job. So we are working on that particular part, like okay, whatever you're going to invest, or you can say like okay, whatever you can give any name. You can just give it's the name of the charity you just want to help someone else, or you just just want to help yourself also. If you want to just thinking like, okay, you want to buy this bundle for yourself, and then whatever the money that's going to help someone else, so it's going to be in that particular way. The community which Prerna was talking about, so the community in the sense, so the people who are the part of this particular bundle, so even if you spend 10,000 rupees, we created a course there, then it will come back and become the part of this particular bundle. That means you are helping everyone who's in the community, in at least they're not going to pay anything. So that's the thing we are planning right now. Yeah, I think it depends on you, like, okay, how you want to choose, like expertise. They decided they will go with the scholarship base. That's okay. If you have some other criteria, and if you want to share with us, just let us know. If we can help you to filter out on the basis of your criteria, we will do that particular thing. Yeah, so I think, Prerna, we are
Okay.
almost done now.
All right. Thank you, Puneet.
Yeah.
Right. So um, is Ramdas
Yeah,
in?
Ramnath is here.
Yes.
Yes, yes.
How are you? How are you feeling today, sir?
Yeah, hi Prerna, I'm here.
Yes.
I'm
How are you feeling, sir?
Yeah, I'm feeling better.
Right. So guys, he was down with high fever, but he made it to the session. Thank you so much, sir. Sheer honor to have you at ExpertTalk. Right. So give me a couple of minutes, sir. Let me just go over your brief introduction of your profile overview, and I'm just going to, and then hand it over to you.
Sure.
So Ramdas Mozikunath, he is a guru in verification engineering. Um, uh, he's an experienced design verification engineer with 20 years of experience in pre-silicon and post-silicon verification of complex ASIC and microprocessor, with a passion for continuous learning and improving. He has vast experience in different verification methodologies and programming languages like System Verilog, C++, OVM, UVM, etc. His expertise includes microprocessor cores, caches, coherency, and memory subsystem, microarchitecture, and verification. He started off as research engineer at CDOT, involved in system level design and debug for ATM telecom switches. He joined Intel Corporation as design verification engineer, involved in verification of Intel's first integrated memory controller. Worked on, excuse me, just 1 minute, sir.
Yeah, sure.
Okay. So he worked on test bench, stimulus, checkers, test plan, and collaboration cross-site. He later moved on to an advanced role in design verification, owning complete verification of load store unit, became the first member on DV team. By DV is basically design verification team, helped in building credibility across cross-site teams and mentoring others. In next 10 years, Ramdas executed various roles in design verification as staff engineer, advisory verification engineer, senior verification engineer, PMTS role in design verification. He's a well-known blogger, instructor, and writer, and has his own website called Verification Excellence, where he shares comprehensive knowledge around verification, system verilog, assertions, and UVM. He's an active Quora answer writer on VLSI and related topics. He has been recognized as Quora top writer, and was recognized in 2017 and 2018. He has co-authored a book on cracking digital VLSI verification interview success, a golden reference guide for verification engineers at all experience levels. All right, sir, I'd like to hand it over to you now.
Okay. Yeah, thank you, Prerna, for that nice introduction.
Thank you, sir.
Thank you, VLSI expert, for giving me this opportunity to talk today. So can you just confirm that the screen, what I'm sharing is visible?
Yes, sir.
Okay. So let's get started in the interest of time. So today I'm going to talk about the practical verification of a modern CPU design. So I'm going to skip the introduction. I think Prerna already gave me a nice introduction. So in this talk, I'm going to cover some details about how the modern CPU SoCs looks like. I think earlier today, I think Advait gave a good talk about the history of computing, and I think some of you would have got a clear picture of how the complexity of computing is trending. So I'll talk about some of the modern CPU SoCs, what are some of the complexities, and then specifically in terms of how to verify some of these CPU SoC designs, what are the challenges. Then typically when we learn about verification, we hear about IP, SoC, CPU. So we'll just quickly touch about what is the differences between IP, CPU, or an SoC verification. We'll talk about details about architecture versus microarchitecture verification. And then we'll also look at some of the focus areas and standard practices that we do, especially in the industry when we kind of deal with some complex design verification. So I want to start with this diagram, which lists a bunch of modern CPU SoCs. I think most of you should be familiar with the chips that I have listed here. So if you see here on the top, you have the Apple A12 chip, which is one of the CPU that goes into all of the Apple's iPhones. And then you have on the right, you have the one of the recent ARM's high-end Cortex series of processor, the Cortex A76, which is also one of the high-end CPUs designed by ARM. And that is kind of used by a lot of companies, especially for their high-end mobiles. And then down you can see the Qualcomm Snapdragon processor, which also goes into high-end mobile phones. And then on the left side, you have the Intel Core i7 and the AMD Ryzen. These are again two powerful CPU SoCs that goes into a lot of desktops as well as laptops from Intel and AMD. And on the middle, you can also see the new RISC-V CPU. So I think many of you might be familiar. RISC-V is a new open source based ISA, which is getting a lot of traction. Various companies are building CPU designs based on the RISC-V ISA. So that's a new trend of CPUs that is getting designed. And if you see all of these are all like complex CPU SoCs, which has like several things in common. And one of the most common thing is like everything now has like more than one cores. I think we have gone past from designs which have like just one CPU core where you just run one core, one program runs on that core. We are talking about anything from 2 cores to 4 cores, 16 cores, 32 cores, and even some of the high-end server class CPU designs from both Intel and AMD right now offers like 64 cores. And then some of the new generations will go to 128 and more. So these are all trending to be more and more complex with many, many CPU cores integrated on a chip. And as we have many CPU cores, then also comes with the problems of having caches and memory along with the CPUs. So I think some of you should be familiar with what is a cache memory. A cache is a small memory that is kind of placed very close to the CPU core, which kind of hides the memory latency, such that any CPU core, when it executes instructions, it doesn't need to have a long memory latency to fetch the instruction. If the instructions are already prefetched to a cache memory, which lies very close to the CPU core, then the instruction can be executed much faster. So with increasing number of cores, there will also be increasing number of caches. And then there is also the problems of keeping all the caches across these cores to be coherent with respect to data. So all of that adds like additional complexity to some of these multi-core CPU designs. Additionally, all of these also has like several high-speed IOs. So be it like high-speed IO to talk to the memory, like high-speed DDR, DRAM memories, or maybe like high-speed IOs like PCIe or any storage interfaces. So those are all additional complex parts of the modern CPU. Additionally, I think I think Advait also talked about something about the different kinds of packaging techniques happening. So we are not just having single package to have all of the CPUs. I think there are like various techniques where you also go from a 2.5D to or a 3D packages. We are also talking about chiplet based designs where you kind of have like multiple chiplets designed and then you package those together in one single package. So we are using all of these techniques to create some of the modern CPU SoCs. So I just wanted to give a feel of some of the complexities. And then to get all of these implemented in terms of both design, verification, as well as the physical design, I think there's like a lot of complexity and a lot of hard work that goes in the industry. And in today's talk, I will specifically cover about how the verification of this is complex and what are some of the things that we do specifically. So before we go into some more details, I wanted to just briefly talk about what is an IP, what is an SoC, what is a CPU. Just to get clarity on the terminologies, because sometimes the terminologies are used interchangeably. So if you see this diagram, I think this is a diagram that I picked from one of the ARM-based SoC. So you can see here there are like two Cortex A57 and A53 processor. There is a GPU, and then there is a coherent interconnect that kind of interconnects all of these CPUs, GPUs to some peripheral interconnects. Then there is other direct memory controller that talks to the memory. Similarly, there will be IO interface, and then there's like interface to the display and the video controllers. So if you see, this is treated as like an SoC, and then you can see inside the SoC, there are like CPUs. And then the way I see IP is like an IP is like a logical block or a functional block which has its own defined interfaces. So in that way, if you see any of the blocks in this diagram, I mean, logically we can call it as an IP. For example, the CPU itself can be treated as an IP because that is kind of a one logical block by itself with its own defined interface, though it contains its own sub-blocks. For example, here inside the CPU, there might be like blocks like instruction, fetch, decode, and execution. Those itself could be smaller IPs. The L2 cache can be treated as an IP, and then the CPU itself can also be treated as an IP. So that is what is an IP is. And then the CPU is more like a general purpose hardware. General purpose hardware is where like you could use that CPU, which is like very general purpose, and then execute any program which kind of runs on the specific instruction set that CPU implements. And then the SoC is like the collection of various IPs, which could be a set of IPs, and the IPs could also be CPUs, GPUs, other processing elements, and anything else in that way. The SoCs are normally connected using some protocol-centric interconnects and interfaces. So that's where I think a lot of protocols that probably people come across, like the AMBA protocols like AXI, the ACE, the CHI interface, and all of those protocols, plus even the DDR interface, the PCIe, Ethernet, and all of that interface kind of are used to interconnect some of the components when we build an SoC. So I wanted to just give a flavor about what is IP, SoC, and how these are all these building blocks are built together to form an SoC. And now let's look a little more inside what is there inside a CPU. So I wanted to give a simple view of a single core CPU first on the left side, which is something all of you would have learned in your engineering if you have learned any of the basic computer architecture course. CPU, I think you would have also learned like a single CPU core executes instructions in a pipeline, where basically you will fetch the instructions from the memory. And once you fetch the instructions from memory, you want to decode those instructions. And then you feed the instructions to ALU, which is basically executing. Now, this is the simplest view of an execution unit. And then once you execute whatever is that instruction, then you kind of feed it to a memory path where you will either write it back to the memory. And yeah, so that's a simple pipeline of a single core CPU. And then this single core CPU is what kind of is still used to build a multi-core CPU, which is what is currently the trend. Where what we do is like we build several of such CPU cores. And here I've shown an example where there are like 4 CPU cores. So each of the CPU core will be, let's say, one pipeline as shown on the left diagram. And then, I mean, I think modern CPUs are also more than one single core. Those are also capable of simultaneous multi-threaded execution. And what I mean by that is you can also execute multiple threads in parallel on one CPU, where the number of threads I think could be 2 or 4, or I think even some of the recent CPUs can support even up to 8 threads running parallelly. And then the CPU will have a set of caches associated with that, basically to hide the memory latency. So typically we have like 3 levels of caches. There will be an L1 data and an L1 cache, I cache. And then there will be a shared L2 cache, a level 2 cache, and there will be a much bigger shared level 3 cache. And then that kind of talks through some interconnects to the memory. And yeah, it talks through a memory interface to the DRAMs. And similarly, there are high-speed interfaces through which you can also connect to other CPUs, where you can build scalable system which has like multiple chips, and that can be used for building larger server class designs. So yeah, so that's how the modern CPUs are kind of trending to. I think most of them are currently multi-core designs with at least 3 levels of caches, a high-speed coherent interconnect that deals with connecting with other similar chips to build scalable systems. And then you also has like high-speed interface talking to your DDR memory. And yeah, and as I mentioned, since we have like different levels of caches, we also need to ensure that all the caches are coherent, because let's say in this example, there are like multiple CPUs and each CPU is executing its own program. So the CPU might fetch those instructions as well as data into its level 2 cache, or if it has, to its own private cache. And then sometime later, if there's another CPU is running the program, and then if it wants to fetch the same data, it needs to make sure that if say the original CPU had modified that line or the address, then it needs to get the correct data to operate on that such that the memory is coherent. So with multiple levels of caches and with multiple CPUs, there is always this problem to ensure that caches are coherent. And that itself is like a complex portion where some of the common protocols that we use, at least in standard designs, are like the AMBA, ACE, and the CHI protocol, which kind of fundamentally implements some of the messy, noisy kind of protocols, which I think some of you would have learned, especially if you have taken some of the computer architecture courses, where we kind of has to remember the state of each cache line with respect to the memory, whether the line is kind of valid data or a modified data, or it's shared across multiple caches. And based on some other protocols, we need to make sure that all the caches are coherent, because otherwise each of the CPU might be executing on some wrong data. So that is another big portion of ensuring to be functionally correct as part of the design implementation of multi-core CPU designs. So I wanted to mention that as well. And then now let's go into a little more details about specifically how some of these are verified. So I think a lot of people who have, you would have learned about theoretical verification. I think people would have learned about IP verification, which is, I think, is common thing that many of the entry-level engineers start with. So where we kind of take a logical block or a unit, which could be a collection of design units. And here I listed some examples like an Ethernet MAC or a PCI bridge or a USB controller or a DRAM controller. So these are all blocks by itself. And how do we verify some of these blocks? We use standard verification methodologies, typically whatever system Verilog, UVM, and all of those methodologies. We use simulations, we use constrained random and coverage driven approaches. And the focus of the verification engineer will be to make sure that the implementation, the design implementation of the IP with respect to the functional specification meets the functionality, and the IP as such functionally behaves correctly. So that's the smallest level of verification that we do. And this still forms the building block for higher CPU as well as the SoC level verification. Now, on the other end, SoC verification, as I mentioned, SoC is a collection of logical blocks. An SoC can have one or more CPUs as well. And additionally, it can also have like other processing elements like GPUs or DSPs or any of other processing elements. Plus, it can also have like IO subsystems and all of those. And the difference between IP and SoC verification is that a SoC verification, especially now that SoC is like a huge design and not just like a small IP as it's by itself, the focus of verification shifts from not just looking at an implementation, but we kind of focus more on a system level scenarios where the end-to-end scenarios are functioning properly for that SoC. We also make sure that the interaction between various IPs are proper. We don't focus as such on an IP verification at an SoC level, because that's something the SoC verification assumes that the IP verification engineer has already done a good job. The kind of issues that are expected to be found at SoC are if there are any kind of miscommunication between, say, two IPs, and then if those are not connected properly, or if some of the interconnects has some issues, or if there is any kind of miscommunication. I think those are the scenarios that kind of come at SoC level. But then SoC verification is also very important, because finally the SoC is what gets taped out, and that is what goes as a functional product to an end customer. Now, the CPU verification is kind of a mix of IP as well as SoC verification. Now, there's also the CPU versus core terminology, which I think is interchangeably used sometimes by people. But the way I see is like core is a single instance of compute that can run one program. And as I mentioned, sometimes the core itself can be multi-threaded, also known as simultaneous multi-threading, where the core itself will be internally, the hardware will be designed such that you can run like more than one thread parallelly. And the CPU as such can have like one or more cores. Anything from 2 to 64 cores has become very common. And then I think the designs that will come mostly in the laptops and high-end servers is going to see this trend increasing at least in the next few years. And when I meant by CPU SoC is multi-core CPUs, which has this several CPUs. And then I talked about caches and interconnect, which are very crucial to get this multi-core CPUs running parallel programs at the highest performance. And then we also need an IO subsystem and a memory subsystem that can feed all of the CPUs with the right set of data from the memory as well as from the IO side of the system. So all of these together forms the CPU SoC, and we'll see some of the challenges and some of the aspects of how the CPU SOCs are verified. So let's start with some of the challenges that we normally see verifying CPUs. So as I mentioned, CPU is like a general purpose hardware. So it's supposed to be executing any program that anybody writes in the world, right? So if somebody writes a software program and then we want to run it on that CPU, then it should just work. And how do we verify that every software program that is in the world works on CPU? So it's kind of almost practically impossible to take every program and then run it through a simulation and then make sure that whatever CPU we are designing is functionally correct before we kind of take out. That's kind of impossible. So we can never do that. The other parts we'll come to see how we address that and make sure the CPU design can still deal with any software program that can be run on it. The other part of the challenge is the complexity in terms of microarchitecture. I think the current CPU designs are all superscalar. The instructions gets executed out of order. There are multiple pipelines. There is branch predictions and several other complexity in microarchitecture. And then I also talked about cache coherency, memory ordering, and memory consistency aspects, especially when you want to run with parallel programs. Then there is also this increasing emphasis on performance and power. I think we all know we always want to buy any CPU which has the highest performance. Whether we look for a laptop or whether we look for a mobile phone, we always look that the power consumed is the lowest and the performance is the highest. So that is still the trend in the design. And then recently, I think sometime from last year, you also have seen there is an increasing trend of security being addressed in designs. Especially, I think sometime last year there was this attacks called Spectre and Meltdown, which are some of the challenges at least Intel faced in terms of some of their designs kind of getting leaked in terms of, especially with speculative execution, people were able to leak out some of the data from the processor. So I think from then onwards, security has become a new dimension, and then that is also added as a challenge to verification. The other part I wanted to touch upon is architecture versus microarchitecture. I think this is important, especially with respect to a CPU kind of design. But even otherwise, for any kind of design, I think this is important to understand. An architecture, I think, describes a high-level attributes or feature of a system. So it's you can treat it as a hardware-software interface. For example, that is how hardware is defined in terms of architecture. And then when you want to write a software that runs on the hardware, then the software engineer needs to understand architecturally what are all the attributes, what are all the features that are supported by the system. So that is what is defined in architecture. Now coming specifically into a CPU, so this kind of covers the instruction set architecture, also known as ISA. So this basically collectively describes about the various instructions supported by the design, the different kinds of registers and memory models, interrupts and exceptions, and also the programming model that a software engineer needs to follow. Some of the common instruction set architecture that are popular right now is x86, which is what the Intel and AMD CPUs are built on. Then the ARM V8 and I think recently even V9 architecture. So that kind of is what the ARM designs follow. And then I mentioned about RISC-V, that is a new open source ISA. I think that's still in the early stage, but I think that's going to see a lot of interest in the coming years. And then MIPS and Power was another two popular ISA, but kind of getting little less interest, especially with ARM and RISC-V becoming more and more popular. On the right side, microarchitecture. So microarchitecture talks about the details about implementation. So this talks about the actual hardware implementation in terms of what are the units, subunits, how do we define the actual RTL units or modules, what are the interfaces, what are the state machines, what are the different data structures to be used, how is the pipelining, do we do symbol execution, in-order execution, and out-of-order execution, branch prediction, caches, coherency implementation, and all of these kind of details about the actual implementation goes in the microarchitecture part of the design. Similarly, the instruction decode. Yeah, similarly, the instruction decode and the microcode. So all of these kind of falls under the microarchitecture with respect to a CPU design. Now, when we do CPU verification, specifically, we focus on the architecture and the microarchitecture separately. Now, I mentioned that it's practically impossible to take any software program and run it on a simulation and make sure that the CPU works for that design, for that program. So what we do is like, we want to make sure that whatever the CPU's implementation first meets the architecture definition. And what I meant by that is that the design has to be compliant with that instruction set architecture. So the instruction set architecture defines all the instructions that are supported by the design. And a software program is going to refer to that same ISA and write what are software programs. So we want to make sure that all of those instructions defined in that ISA in all the different modes are kind of functionally verified. We also want to make sure all the memory management models, all the interrupts, exceptions, everything that is defined works properly. So there is a lot of emphasis in architecture verification to make sure that the design is compliant with the ISA. How we do is that we create random instruction sequences or generators. So you can think of this as a stimulus generator in your typical verification methodology. Primarily, we develop this in a high-level language, which could be something like C or Python. And occasionally, we also use inline assembly code, especially if you want to get like better control on a specific sequence of instructions. Now, so we do this and we kind of generate thousands of random instruction sequences and then functionally run it on a CPU simulation to make sure it's functionally correct. Now, the other part is how do we make sure, yeah, you write all of the sequence, but how do we make sure it's still, your design is meeting the correct specification? So what we normally use is like, we also build an architectural simulator, which is also called an instruction set simulator, which kind of comes normally with most of the ISA. Some of those people have already developed for popular ISAs, and some of the new architecture like RISC-V, I think it's open source and is available in open source community as well. So we kind of run our program through this architectural simulator, make sure it's kind of generating the correct results. And then we also run the same through an RTL simulation and then kind of compare and correlate to make sure the correctness is, to ensure that the correctness between the architectural simulator and the functional simulation is met. Now, typically architecture verification runs into thousands of tests. And I think some of the companies like Intel and AMD, I'm aware, like it's not even thousands. I think there are like lakhs of tests because these companies has like decades of CPU design, and then the test as well as the instructions has like grown over years. So it's always a challenge to make sure we run all of these I don't know, tens of thousands and up to lakhs of tests in simulation before we kind of tape out. So this is typically done at a CPU or a core level test bench. And this forms one of the big chunk of verification time for a CPU SoC goes in the architecture verification, but it's kind of crucial to make sure it's compliant with any ISA that the design is targeted. So moving forward, the other part is CPU microarchitecture. So in addition to just ensuring that the design is compliant with ISA, we also want to make sure that the microarchitecture is verified thoroughly. Because if the microarchitecture is not verified, if the microarchitecture is not still verified properly, maybe some of the instructions might work, but maybe eventually when the design goes to a customer's hand, and then if they run some large program, there could be still an underlying corner case bug that might still show up, and then maybe you might see an occasional hang or an occasional failure in your system. So there is still a lot of emphasis on microarchitecture verification, where we go into a white box approach where we understand the design, we focus on the implementation of how the design is done. We go and do block level and a cluster or subsystem level verification. For example, going back to this again, same example, we might build a smaller test bench for like just the instruction fetch and decoder, and then verify it thoroughly using any of the standard verification approaches like constrained random verification that uses some of the popular system Verilog and UVM based methodologies. We also use a lot on the functional and code coverage techniques that are used for a block level verification. We could also use formal verification, because now that we are talking about smaller block level verification, for some kind of a design, it becomes like much faster using some of the formal techniques to get a faster verification closure. So we also focus a lot on the microarchitecture. Generally, when the design starts, we focus on smaller blocks, thoroughly verify them before we kind of start putting together a CPU or a block level or a subsystem level design, and then go into a more architectural as well as like a microarchitecture verification at the top level. The other focus areas that we do in the verification is, I think, a lot of things, especially on the power management. I think there's like a lot of features that goes into most of the CPU designs. Especially, I think many of the architectures defines like different power states and power saving techniques. Some of the common things I think you will be familiar is like when you put a CPU or a laptop into sleep or a hibernate mode. So when we put into the any of these mode, then automatically there's like the CPU kind of goes to a lower power consuming state, even though it's not like fully shut down. And then there's like a lot of design flows that gets kicked in to kind of get into this lower power states. And we put a lot of emphasis to make sure all of these flows are functionally verified. We also put a lot of emphasis on verifying the DFT and the DFX parts, because that's what determines how well we can test the chip after manufacturing. We also put a lot of emphasis on performance verification. I think a CPU is not, it's only good if it's kind of very much performance competitive, because right now everybody's aware of comparing CPUs. And if you think, I mean, I think people know how to compare what is the instruction per cycle, what is a single threaded versus multi-threaded performance. So those are all very key performance metrics. There are various benchmarks, some of them like SpecInt and SpecFP and LMBench. The memory latency and bandwidth, all of these are very key performance metrics that goes into the design aspects, and then we also put a lot of emphasis to verify and make sure that it meets kind of the design specification. Additionally, I mean, I think with designs getting increasingly bigger and bigger, there is also an emphasis on doing system level verification, especially using emulation, where we kind of run long running stress tests. And even some of the designs, we make sure that we are able to boot even some of the OS like Windows and Linux before we even tape out the design, because that's kind of very crucial. So we don't want to miss any bug that kind of prevents somebody to boot a Linux when we get the first chip back in the lab. So there are like a lot of such focus areas. And I also wanted to go through quickly on some of the standard verification practices. I think if you would have gone through any of the theoretical verification courses, I think these are all standard practices that anybody does for any kind of a design. So I think you should be familiar that all the verification starts with test planning, which is the starting point for verifying any design. And then the verification methodologies itself is like a broader topic where there are different kinds of methodologies that can be applied for verifying. So there needs to be a correct call based on what methodologies to apply it based on what kind of design. And then once we identify a methodology and then we define a test bench architecture, the test bench needs to be architected in a proper way to make sure that the verification can be done the most efficient way in the least amount of time that is possible. Then regressions and debugs are one challenging area for a verification engineer. And I think I would say at least 60 to 70% of every verification engineer's time goes in regressions and debugs. So that is one area I think a lot of emphasis goes. And that is also an area where there's like constant scope for automation and innovation. And I think that is going to stay there at least in the foreseeable future. The coverage closure is another very challenging area, especially now that we are talking about huge designs where you cannot just write directed test and ensure everything is working. A lot of time we approach using constrained random stimulus, and then we also have like this huge coverage to be closed before you can tell that the verification is complete. And then there are like different kind of approaches used to ensure the coverage closure can be done in a faster way. So that is another area which is theoretically very wide, but then there are like practically we kind of apply a lot of techniques to get to a faster closure. Bug hunting is another area because, as I mentioned, verification, we can never tell that a verification is complete because there can always be something that we might miss because of the kind of complexity of the designs. So a lot of emphasis is put just to hunt for bugs and then discover as many bugs as possible before we kind of tape out. And automation is another area I think that kind of crosses with everything. I think it's kind of getting more and more important. And I think you would also start hearing about some of the new AI, ML kind of techniques also being applied in verification and in general VLSI design to kind of enable or simplify some of these practices. So yeah, I just wanted to briefly touch about some of these practices and why some of those are like important. Okay, so I will just think I'm already at time or 1:13. Yeah, I will.
Yeah, Ramdas. So you can do it. So I think.
Yeah, I will try to wrap it up a little faster.
Sure.
Yeah, I think test plans, I think we already talked through briefly, so it's kind of fundamental for any good verification story. I think a good test plan is what sets the base for a good verification. Everything that needs for a proper verification needs to be planned correctly and then needs to be captured upfront. Methodologies and test bench architecture. So I talked about the same thing. This is where a lot of thoughts goes upfront, where we understand the design and then figure out what is the right methodology for what kind of designs, which portion of the design can be verified with simulation, which can be verified with formal, where can we use emulation, what are the different aspects of power that needs to be verified separately. So all of those needs to be thought through properly, and that needs to be fed through before we even architect a test bench. Regressions, I mentioned, so regressions is always a challenge because we always has like huge collection of tests to be run. This is important because especially when a design is progressing, we don't want to be running the same test every day. You kind of get some test passing today and then maybe like 1 month later, you don't want to be in a situation where the same test is broken, right? So we want to always continuously go in an upward direction where the quality of the design improves. So that's where the importance of regressions comes. As we kind of verify some feature, we kind of add that test into the collection. And then we continuously run this collection of tests and make sure we are always improving the quality of design. And then, as I mentioned, there's like huge tests, especially for architecture verification, microarchitecture verification. Again, different blocks might have different test suites. And then we need to constantly run all of these tests throughout the design lifecycle and make sure that at the end of the design lifecycle, all of these collection of tests are passing such that we have a confidence in the design. So that's the importance of regressions. The debugs is the other key area that practically, I think, takes a lot of time from every verification engineer. So normally a debug is basically the first step. First step of debug is like detecting a failure. So when we run a test case, we need to find a mechanism by figuring out how that test fails. So typically we have like assertions, checkers, scoreboards, or timeouts and all of those, which kind of helps to figure out a test failed. And then once you have a test failing, then the next step is like, how do we root cause the failure? Now the root cause of failure is only possible if you thoroughly understand the design and also you understand what is that you're trying to do. So some of the things are like, yeah, you have to understand the failure and then locate the cause. The failure could be either in verification or in design. Sometimes it takes like multiple iterations. We might need to look through some of the simulation waveforms. We might need to understand or talk with the design engineers. We need different debug tools like monitors, log files, waveform viewers, everything to kind of functionally identify what is the problem. So this is a very time consuming, but it is also one area where verification engineers spend a lot of time. It needs a lot of patience to debug a failure. But then once you develop this patience, then I think that is what will take you from a basic or a beginner engineer to someone who can kind of start dealing with much more complex problems. And I think I will just have one more slide. I think I also wanted to mention, we also look at a lot of metrics in the verification. As I mentioned, there's like a lot of scope for verification to be complete. We have like huge collection of tests. We have coverage to be collected. We want to look for bugs and all of those. And with the kind of complex designs, I think there is always more and more to verify, but then we always have like less and less time as the complexity of project is increasing. And the other thing I have learned is like we always need to be paranoid because we can never be confident even after doing so much of verification that the design is bug free. So we always needs to be paranoid, thinking that there is always a bug in that design, and we continuously look for that bug to be discovered. So some of the metrics that we look for completion are test plan completion. Test plan is still the fundamental thing. So once we get a proper test plan, once we review it and then make sure all the planned items are completed, that kind of gives us some confidence. Then we also need to look at the simulation-based metrics, where we look at the regression pass rates, the bug trends, the bug rates, historical trends, comparing the bugs with the current project versus previous projects. We have to look at the functional coverage trends, code coverage trends, and we also look at some of the code stability. And all of these metrics are monitored closely before we can even tell that the verification is complete. So this is again like very important, and I think it's it kind of has like a lot of emphasis in industry. So I think I will stop at this point today. So if there are any questions, I can take it.
So Ramdas, there are a couple of questions on the chat. So if you want, you can just check those chats directly.
Okay.
So I think Senthil asked first question at 12:54. So you can just check that particular one.
Okay, I'm trying to get the chat.
Else I can read the
Yeah,
chat.
okay, I'm just. Okay, so I can see. So I think what skills are needed for VLSI verification engineer, 2 or 3 years experience in IP verification? Yeah, I mean, I think, so when you start, I think right now, I think most of the people are, at least people expect they to know at least one of the languages like system Verilog. And I think methodologies like UVM has become so popular that especially there's like so many people who know verification with system Verilog and UVM. So those are considered to be very basic. Anything other than that, I think it's still the fundamentals of digital logics, some computer architecture, and then maybe a general awareness about some of the modern kind of designs. I think not everybody expects you to know about 5G or automobile or those. I think a general awareness is always a plus, but then people still look at your fundamentals in digital design plus programming and some of the verification focused system Verilog and UVM. I would say that's what will get you started. Yeah, and I see is Edge AI self-trained verification engineer. Is Edge AI self-trained verification engineer more probability to work with upcoming AI-based processor teams? I didn't really understand that question. So I'm going to skip that one for now. Then next question from Rohila. My question is, how can we introduce the machine learning in verification domain to handle complex verification scenarios? Yeah, so I think machine learning is still an early stage. I would say, domain. But then there is also a lot of interest, and I can tell that at least every company or several companies that I know has like internal work groups that kind of looks at machine learning techniques, and then they're trying to see how that can be applied to various parts of verification or even general VLSI design. Specifically in terms of verification, I was telling, I think regressions and debugs as one area where verification engineers spends a lot of time, especially given the large set of test suits that we deal with and the large amount of time that we deal with in terms of debugging. So people are exploring some of the algorithms in ML to see if we can find out the optimized test suits or find out if we can automatically triage and root cause some of the failures. So I think it's still too early, but then there is like a lot of emphasis, and I think every company is investing in that, especially to solve some of the verification problems. Machine learning. Yeah, it's machine learning. Yeah, it's also kind of, I mean, it's still kind of explode in a little early stage, but then yeah, some of the writing some intelligent sequences, trying to automatically close some of the coverage, not wanting to run like thousands of tests, but then trying to figure out the right constraints. I think those are all some areas, definitely some of those machine learning algorithms are being considered. I think tips, I think I would suggest, as I mentioned, is like, I think, and especially if somebody is looking at entering a verification area, I would suggest like at least you should learn at least system Verilog and UVM. At least you should have one programming language, and you should be thorough with your digital logic design. I think those are still the key. What are the protocol knowledge expected from a fresher? So again, I mean, I would say like the protocol knowledge is not a mandatory thing that is expected from a fresher. Now, sometimes it can give you an advantage. I mean, I think as a fresher, I think we still look at people who has some understanding about a programming language, system Verilog, UVM, and a strong base in digital logic design, because that is what will get you started right from day one. A protocol could be learned easier. Once you start working on a protocol, I would say that's not a hard one. But then, yeah, I mean, I think if at all you get time, I would suggest like learn some of the basics of the AMBA, especially at least the AXI or the ACE kind of protocols. I mean, you don't need to learn in depth, but then a general understanding about what is that protocol, what kind of systems uses that protocol, what are the different commands or transactions. Just at a high level will definitely help. But then other than that, I don't think anybody expects you to be thorough with any of those protocols. How the cache memory is decided for a particular SOC. Since we have L2, L1 cache that are small and works faster, so why there is a need for shared L3 and L4? Yeah, so the levels of caches L1, L2, L3, and some design also has level 4 cache. So it's a compromise between the area versus speed, right? So the L1 cache typically sits very close to the CPU core, and then the latencies are typically in kind of 1 or 2 clock cycles. So a CPU can kind of fetch an instruction every cycle from an L1 cache. Whereas if it misses an L1, then let's say you don't have an L2 cache, and if it has to go to the memory, then that's like thousands of cycles of penalty. Whereas if there is an L2 cache, the L2 cache typically is little bigger, but then it is not so close to the CPU. And typically it has like memory latencies of like tens of cycles. And then if you have some data already prefetched in L2, then having an L2 cache is still better than going all the way from memory. So it kind of saves still a lot of memory to keep the CPU's pipe filled. So that is the advantage of having different levels of cache. Whereas if you put a bigger L1 all the way close to the CPU, then that kind of defeats the purpose, because then you cannot have even the L1 cache faster, because the bigger your cache is, then your access time also increases. So it's a trade-off between how fast you want to hash and then how much of area and power you want to burn. Which methodology gives best functional coverage? I think there's no specific methodology to be that can be mentioned. So functional coverage is normally used when we do constrained random and coverage driven verification. The key is to identify the correct set of functional coverage monitors and then have the correctly designed constraints and sequences such that you can close the coverage faster. A lot of time people just write coverage monitors for the sake of writing it and then struggle to close the coverage. And especially when we come with large designs, that becomes like an overhead. So there's like a lot of attention that we give in reviewing and then simplifying some of those. So I think it's a more practical aspects of how do we correctly come with the right set of coverage and how do we close it faster using efficient stimulus. Give a brief and regarding correlation between verification and physical design. I don't think there is anything that that needs to be correlated between verification and physical design. The verification focuses on the functional correctness and physical design is focusing on the implementation. Now, both of those happen hand in hand during your design lifecycle. And yeah, based on that, the design changes and then some of those has to go back and forth. Where do you see System C in the future of CPU modeling and verification? I think System C is still used in pockets of design. It's not so widely used, even for, I think some of the CPU modeling does use System C, but those are more for the system aspects of the CPUs. I feel that will continue the same way because there are some advantages of System C, especially to model system level aspects. And yeah, but I think it's not really used much in verification. It's more used for system level modeling of CPU based systems to get some early performance data from your design. I think I'll skip this question. I think I'm going to skip some of the skills because I think I touched upon some of those. Okay, I think I will stop here. I think we have already overshot time.
Yeah, thank you, Ramdas. I think that there are almost you covered all the questions. So there are one or two questions. Maybe these people can listen back to your the presentation, so I can see the skills and all you have covered in your presentation. So guys, you can go back and you can just listen. I think then you will get your answer. And there are a couple of questions I can see. Those are like that will take a lot of time. So maybe we can. So we are planning to have something like where we can have more Q&A session. So we will give the time for the Q&A session from the next talk onward, like a little more, so that we can address everyone's everyone's question from the next time onward. Thank you, Ramdas.
Thank you so much, Ramdas, for an excellent session. And please take good care of yourself.
All right, thank you.
Right, so that brings us to the end of the session. We want to thank you all for joining us today. I want to personally thank the attendees who are hooked onto the session throughout and spending their Saturday afternoon with us. You guys are amazing. We'll be back with 3 new experts in our next session on 17th October, the third Saturday of the next month. And lastly, a profound quote with which we would like to conclude the session. Thoroughly conscious ignorance. Thoroughly conscious ignorance is the prelude to every real advance in science, by John Maxwell. Take good care, stay in, and see you next month.
Bye everyone. Thanks a lot. Thanks Prerna. Thanks Ramdas.
Thank you, Puneet.